Now to be in time, let's start. And so I kindly ask the speakers not to exceed a quarter of an hour, including questions. And two of speakers are here, so let's start with the first talk. Uh,
Mhm.
Malik, you may start.
Yeah, okay, thank you. So today we are talking about traffic management algorithm for V2X based flying fog system. Uh, First of all, about 5G and V2X technologies. 5G typically promises a very high bandwidth, ultra low latency, and very high reliability. With these promises, it becomes evident that technologies, specifically with 5G, that can be leveraged in vehicles. V2X lets vehicles share data in real time to avoid accidents, coordinate traffic, and become more aware of the surroundings. V2X leverage sensors and computer vision for non-line of sight awareness, effectively allowing cars to see what humans drivers cannot see. V2X will not only provide low latency communication, but it can also enhance safety and improve awareness and enable reliable and seamless autonomous driving. Uh, the overall idea of V2X is that a vehicle is able or will be able to use its onboard communication tools to deliver real-time traffic information, preemptively react to changing road conditions, recognize and signs and warnings, and more. V2X system supports a large number of new services and protocols. Therefore, moving to integrated interaction with the surroundings information space defined as V2X interoperability should ensure the interoperability of the various networks and systems involved in providing services to users. Here we see at this figure the general architecture that we used, including elements of the physical world like cars, road, unmanned autonomous vehicles, people, and etc. We In this work, algorithm has been researched to help in transmitting and delivering data from the drones, the UAV, to the users in a short time and at a high speed. To transmit data from the users to the nearest controller uh, needs um, needs a fixed amount of energy, and some requests flow may be lost if the controller is already providing data to some users. Requests can be redirected to the cloud server if the controller is busy, or it can be lost if both controller and the cloud server are busy. And this is the main problem of our work. In this work, we use two core models. Each one, the difference between each one is the number of nodes and the average service time. Here we see the structure of the simulation model. Uh, Simulation model of the considered systems was implemented in the program AnyLogic. We have made some assumptions for the simulation model. We suppose that UAV, which is used as a base station in our work, equipped with a controller that provides execution of the request arriving from the user's equipment located in the communication range of the base station. The traffic originated by users presents request flow, which arrives at the controller. Each request may be served by a controller and may be redirected to the cloud server, or may be lost if both controller and cloud server are too busy. We assume that the one cloud server can serve a number of UAV or unmanned autonomous vehicles. We describe the controller as a service system which provides execution of some results simultaneously. For example, it may be a multi-core processor. we use two core models which provide execution of the requests in 1 millisecond. And this is 1 millisecond, it's the average service time. The model of cloud service or the model of cloud server differs from controller by a number of cores. It has 8 cores in the cloud server model, and the average service time, which is equal to 0.5 milliseconds. Yeah. In this work, we chose three cases with different requests rate. It means with traffic intensity. The first case, when we have 8 requests per second, which corresponds to a high traffic rate. It means that when we have 8 requests in 1 second from users, it's a high traffic rate. When we have 4 requests per second, it corresponds to mean traffic rates. It's normal performance conditions. Sorry. And when we have 2 requests per second, it corresponds to a low traffic rate. The results of our work, here we see the dependence of the response delay on the part of the traffic served by a controller. And in our case, it's UAV equipment. We can consider that the first and the last cases, overall, it's like upper and the lower borders of the traffic variations during the functioning of the system. The middle case, which is when we have 4 requests per second, corresponds to the average and the most probable condition of functioning. We study dependence of those parameters on the part of traffic redirected to cloud server. In the result shown in this figure and in this next one, we can see that it shows the dependence of the delay, response delay, and at this figure. Considering the results showing at this figure, we can know that in the case of low traffic, intensity, when it's A equals 2, the delay value increase with increasing of the part of traffic forward to the cloud. This is due to the final throughput of the cloud. In the cases of when we have 8 requests and 4 requests, correspondingly, we see minimal values of the delay. At the point when it's 0.2 and 0.4, this we see the minimal values of the delay. Therefore, we can know that in the range of average and high traffic rate, there are optimal values of the distribution of traffic in this figure. This is the dependence of the power consumption on the part of traffic served by controller. Looking at the results, we can know that the low traffic rate, at low traffic rate, A equals to energy consumption. Energy consumption increases with increasing the part of traffic forward to the internal UAV's resources, and this dependence is close to line function. We also see the mean and high traffic intensity maximal values of energy consumption. These results mean that the energy consumption in real-life traffic range is not linear and has a maximal value. The maximal consumption point depends on the traffic intensity increasing, the traffic decrease, the p-value, which is the parameter we use for the maximal consumption value. It's clear that if all the traffic redirected to cloud server, that means when the p parameter is 0, the energy spent on the service in the controller is equal to 0. Increasing the part of traffic more than 0.5 in the case of when we have 4 requests per second doesn't affect energy consumption because the maximum load of controller is reached. And after that, it's going down. We see here at the point 0.4. Here we can see the dependence of the losses on the part of the traffic served by a controller. We can see that in this case of small traffic intensity, losses are near to 0. But in other cases, for A equals 4, and when we have 8 and 4 requests per second, losses dependencies are not linear and they have minimal values. For example, in case when we have 4 requests, we can see that the delay in the figure we see in the first figure, this dependencies has the minimal value at the point of 0.4 when we come back here. At the 0.4, it's the minimal value. Presented results show the response delay and probability of losses depends on the part of the redirected traffic. We see that it may be reached the optimal value of delay and loss probability by choosing the correct part of redirected traffic. The energy consumption either depends on the part of the redirected traffic, but this dependence is smooth. The energy consumption is lower if the part of the redirected traffic is bigger, as we saw in this figure and in this one. And show empirical probability distributions of delay, energy, and losses. The conclusion of our work, we have done some experiments through which we were able to determine the amount of energy required for drones to transfer data to users on the road in the case of normal or heavy traffic with different average service time for each experiment. We also experimented the response time to request services depending on traffic state, whether heavy or normal, served by unmanned aerial vehicles. Less energy is used if part of the redirected traffic is bigger. In the short term, we aim in our work to find an algorithm that helps reduce the energy used to transfer data from drones on the traffic roads to the users, and with a short response time, and the percentage of lost data transferred is very little. So thank you for attention. If you have any questions, I'm glad to answer them. Thank you.
Thank you, Malik. Thank you for your talk, and thank you for adhering to the schedule. And I'm sure there will be questions on the presented traffic management algorithm. Please ask questions. I have a question. As I understand, your assumptions, the model assumes multiple access to the system. And what about collisions that may arise in multiple access? Did you take into account some multiple access protocol? There are a variety from Aloha to CSMA-CA. What about collisions?
We used two core models that, like I mentioned in the first at the beginning of the talk. The models are differs. Or the difference between them, it's the core, how many cores in each model. It's a multi-core processor that we used. with two core modules, and this provides execution of the request that we take from the users in 1 millisecond, and this is the average time, the average service time. So with the difference with numbers of cores for each modules, the average service time is equal in our work was 0.5, and it's a very minimal. So with the difference between them, it's one average service was 0.5 and one with 1 milliseconds. And by
Thank you,
that we
Malik.
use, yes,
Thank you, Malik. But if you assume that service system provides execution of several requests simultaneously, this means that the amount of computational resources and energy resources of the system is infinite. Am I right?
yes, you are right.
It's
Because
quite abstract model. It's quite
and because of
okay.
that, we have a limit for the amount of data that can the cloud or the UAV, the unmanned vehicles. We have a limited amount of data that can be received from users. Yeah.
And the second question, speaking about high traffic rate, low traffic rate, and so on, what service do you mean? Voice, video conference, data transmission, and is the model sensitive to the service provided?
If I understand clearly, it means that the normal we have a three. We just make an assumption and chose three cases. When we have 8 requests per second, it means that we have a high traffic range and a high traffic rates, and it means that we have a lot of requests per second to the cloud. And in the normal case, without not in our work, it means that if we send these requests per second, when we have 8 requests, when we send them to the cloud immediately to the controller, and the controller is busy, he can redirect it to the cloud server. And when we both are busy, the data that users sends, it can be lost. And in this work, we use the UAV to take this redirected traffic that comes from cloud server or the controller, and can receive it and give data to the users. So
Thank you, Malik. Thank you, Malik. That's enough. Thank you very much. More questions, please. If no questions, let's move on to the next presentation. I still don't see the second presenter. The presentation identification of narrowband wireless communication. Is somebody from the authors team here? No. If no, we are lucky because we skip the second presentation. Maybe if somebody will join us later, we will give them the floor. But now let's move on to the third presentation. Behruz, are you here? You are welcome. Yes. You are welcome to start. Yes, and we thank Malik for the first presentation for the opening our session. Thank you, Malik.
Thank you for your attention. I'm very glad to hear that.
And now, Behruz, the floor is yours. The microphone is yours.
Yes, thank you, everyone. Can you hear me and watch my screen?
Yes, but not in full
Yes,
regime,
yes. Mm-hmm.
not full screen yet. Mm-hmm.
Yes, it's nice. Yes. Can you?
Now it's okay.
Yes. Hello to everyone. My name is Behruz Danishmand, student PhD at ITMO University in St. Petersburg. I'm gonna to present my paper in the title "Survive of Load Balancing Mechanism based on SDN in 5G IMT 2020." As outlined, we have architecture SDN, benefit and objective of SDN based in load balancing based on SDN, load balancing metrics, load balancing in SDN, distributed and centralized method, type of SDN based load balancing method, and in the finally we have a conclusion. In the screen, as you can see, we have a architect of SDN. At first, I want to a little talk about what is the SDN. Because SDN is a main part for 5G or 6G. And SDN is an emerging architecture that's dynamic, manageable, cost-effective, and adaptive, where control is decoupled from data forwarding and the underlying infrastructure and directly programmed for network service and application. And load balancing is one of the most important tasks required to maximum network performance, stability, and robustness. With the emergence of SDN, as you can see, this is an architecture. Load balancing for SDN has become very important issue. SDN architecture is associated with three main components. The first layer is application, and I choose the laser point. It's okay. Application layer. The second layer and the main as the brain of the SDN is control layer. And the third layer is data forwarding or data plane. This slide, I want to talk about the objective or the goal of SDN based in load balancing and the benefit. Why we use SDN in load balancing? Because lower cost, great scalability, higher reliability, flexibility in configuration, reduced time to reply, automation, and finally ability to build a network without any vendor specific software or hardware. And for goals or objective, the goals of the SDN in load balancing, improve quality of metrics, maximum throughput, maximum response time, avoid congestion, and optimize usage of resource. In this slide, some parameters are required to evaluate the load balancing algorithm and compare it with the previous method in order to specify the better load balancing algorithm and to recognize the advantage and disadvantage. This parameter called a qualitative parameter or load balancing metric. The most significant qualitative parameter or load balancing metric are described as a blue. For example, packet losses, throughput, response time, end-to-end, utilization ratio, overheaded, routes mean score error, and peak load ratio, migration, guarantee bit rate, forwarding intakes, and something like that, and until end, energy consumption and percentage of message deadline flow. In this slide, I want to talk about load balancing that's divided in three groups based on SDN. As you can see, method of load balancing based on SDN divided in three groups: static, dynamic, and hybrid. Hybrid means some of advantage takes from static, and dynamic as better than static and better than dynamic. But at first, I want to talk about static and what is this and disadvantage, advantage, and future, and so on. In a static algorithm, equal division of trophy is done with the server. A static algorithm is suitable for systems with the low load variation. This algorithm needs to have a period information of the system resources in order to be able to make the sure decision of load shifting does not depend on current system state. And about the future, it needs less communication in order to minimize communication delays, where it's reduced the execution time. Weighted algorithm achieve the better response time and processing time. Load balancing methods, the distribution depend on loaded at the time of selecting the nodes before the execution start. Static methods mostly suitable for the constant work application and for homogeneous and stable environment. That produce better results, also a stable environment that can produce better results in this environment. It's easy to be implemented. It's relatively simple to forecast a static method behavior, and it's very difficult to forecast load arrival and processing time prerequisition for future load. And in other side, we have a dynamic. Okay, dynamic is better as a work based SDN as a static. If I want to talk about future dynamic SDN based in load balancing, dynamic load balancing techniques are more effective than static counterparts due to dynamic distribution of pre-programmed load balancing pattern. The proper load balance is crucial to optimize minimum response time, maximum throughput, minimum resource consumption, scalability, and so on. And this feature is very important for us because, as I said before, for yes, benefit and objective, this parameter, for example, minimum response time, response, improved quality of service metric, and maximum throughput is very important for us based on SDN in load balancing. As dynamic is better because has a future better than static method. And dynamic divided into algorithms, distributed and centralized algorithm. In this slide, as you can see, you see two algorithms, centralized in the left side and distributed in the right side. These some algorithms that can use for central algorithm, for example, quality service area algorithm, heuristic approaches, wardrobe load balancing, and for distributed algorithm, routing control platform, server load balancing algorithm, and due to algorithm. And about centralized or non-distributed method, one node receive all requests and distributed them to server. Centralized control implants all of the control panel logic in one place. In such a control, a single server takes over all action at the control level. The main advantage of these controllers are simplicity and control, as they provide single point of controller. Also, this suffer from scalability issue because each server has a limited capacity and handle data plan devices. For a distributed algorithm, all nodes are shared with the distribution of requests. The distributed controller has no scalability issue as an advantage of higher performance under heavy traffic load, because in 5G the traffic is a lot of in comparison with 4 LTE. The data is much more than LTE because we have a IoT and we have every device connected to each other, so the traffic is heavy, so load balancing is important for us. Then distributed is a good and suitable approach for us. And as a hybrid, as you can see in this, in this slide, hybrids, this method are used to overcome disadvantage of dynamic and static load balancing method, and they are used to collect advantage and disadvantage of static and dynamic algorithm to develop a new method. As this, I put a picture about this distributed decision and central decision for more explanation how to work at this distributed or centralized algorithm. Feature illustrate the centralized the right side, where there is a coordinator control which player the load for supercontroller that responsible for ensuring better maintenance for global controller loads info table. There are two essential processes. As you can see, there are two processes involved: the collection of the land information of all controller and ensuring that the load balancing command is sent to overload controller. The two processes can prolong the time of load balancing, so the quality of service, as I said before, all other parameter is low in central decision. But in distributed decision, conversely, contrary with the distributed decision, tend to exhibit similar feature in SDN network when they are connected. In this slide, we have a type of SDN based on load balancing. In SDN, as I said in the two slides about the SDN architecture, SDN architecture has a three main parts: controller, plan, data plan, and application layer. In this slide, in the data plan, as you can see, 1, 2, and 3, it works in data plan because this technique is used to attain load balancing that has a small latency work performance, especially with the data plan. It also used to solve the load imbalance in the path and server and to avoid network bottlenecks in SDN. Data plan can be classified into as a server load balancing, and links load balancing. And two methods, SDN multi-controller and load balancing in IEEE 802.11 standard wireless links, takes place in control layer, and each of them has a another algorithm. For example, in controller panel, a multi-controller or distributed in load balancing, we have three methods: hierarchical, horizontal, and virtualization. For example, in server load balancing in data plan, we have two methods, static and dynamic, and each of them is very feature and advantage of them. And different link selection has a two algorithms, meta heuristic algorithm and other algorithm. And load balancing artificial neural network data plan has also machine learning algorithm, and other algorithm can be used in load balancing based on SDN. In this slide, I want to talk about why we use SDN or software load balancing instead of the hardware load balancing. For software, we have some disadvantage and advantage, pros or cons. Software pros: flexible implementation, great scalability for software load balancing, reduce cost, because in hardware, if new technology comes, we have to replace hardware equipment instead of the old equipment, and load balancing via cloud. In other sites, software disadvantage: when escalating beyond the initial capacity, there can be some delay while configuration load balancing software, ongoing cost for upgrading. In the other side, for hardware or the traditional load balancing that we use in, for example, LTE or other generation for network, 2G, 3G, and something like that, it has two sides, pros and cons. For pros, fast throughput due to software running on a special process, increased security since only the organization can access the server physically, fixed costs once purchased. and the cons require more staff and expertise to configure and program the physical machine. Inability to scale when the set limit and number of connection has been met, connection are refused or service degree until additional machine are purchased and installed. Higher cost for purchase and maintenance or physically network load balancer. Owing the hardware load balancing may also require paying constant to manage. As a conclusion, the load balancing algorithm must consider the current loads to reflect the real-time change. Using signal centralized control can lead to signal points of failure. Load balancing algorithm should be mainly based on distribution decision. Researchers should do more detailed study of distribution architecture to develop better load balancing algorithm taking advantage of SDN architecture. And the last one, as a conclusion, the algorithm should be designed in such a way that it's minimize the latency and response time and maximum their throughput. Thank you for your attention. I'm ready to answer your question. If you have a question.
Thank you, Behruz. Thank you. Please ask questions about the load balancing mechanisms in 5G networks. Do you have questions? Then I ask a question. We know traditional recognized approaches in the area of load balances. For example, the hysteretic overload control to avoid congestion or mitigate overloading both in fixed and mobile networks. This is 3G, 4G mechanisms. And at your presentation, we have heard about the load balancing mechanism in IMT 2020. This is the 5th generation network. Yes. And what do you think, what load balancing mechanism can we take from 5G networks and bring to 6G networks? Because nowadays 6G is on the agenda.
Yes, as you know, 5G started in South Korea in 2018, and many countries, Asian country uses now 5G, but many country, African country and other with low income country do not use 5G. But 6G, yes, will be appear in 10 or 6 or less than years ago, later. And if I want to speak about how to transfer the load balancing from 5G to 6G, I can say the technology SDN. SDN, the main part for 5G and 6G and later, or 7G and something like that. Because SDN can program a device and everyone can work with them instead of hardware equipment. And SDN is the main and very important device in load balancing in 5G, in 6G, and later G in network in the world. I think the SDN, yes, SDN is the main part in the load balancing in the 6G or 5G or 7G.
Thank you, Behruz. Thank you very much for your presentation. I'm afraid we have no time for other questions. So thank you again. And now we have...
Okay, thank you for you.
And now we have the 4th presentation. I see Abbas among the participants. Abbas, are you here? Are you ready to present your results?
Yes, I am here and ready.
Yes, you are welcome. The floor is yours.
Are you hear me?
Yes, you can start, but not full screen now. If you change the mode to full screen, thank you.
Now, hello everyone. My name is Abbas. I'm a PhD student at Von Chevrorovich St. Petersburg State University. Today I will present my topic: multitask multi-UAV computation offloading enabled mobile edge computing systems. Unmanned aerial vehicles are becoming an essential part of 5G and are likely to play a major role in the further functional diversity for 5G networks. It will be widely deployed in surveillance, disaster management, data gathering. The limited resources of UAV's terminals make it
I'm sorry, Abbas. Please,
yes.
I'm sorry, Abbas. Please don't read the text. We all see the text. You may skip the slide and move on to the model or to some more interesting part. We always see the text in introduction. Thank you.
Okay. In this work, an energy-efficient computation offloading algorithm was proposed for multi-UAV-enabled mobile edge computing system to implement multi-level offloading process. The aim of work is to minimize the energy consumption and total task execution time of UAV with consideration of deadline completion and to accomplish the task and energy constraint. The system model consists of multi-UAV connected together wirelessly, and they are connected with base station via a wireless channel. The scenario which has the one of UAVs has a set number of independent computation tasks that needed to be executed locally at UAV, will be offloaded and executed either at one of UAVs to another UAVs, or remotely at each server, offloaded to base station, and the computation will be implemented in the edge server. We has considered two decision variables denoted as beta and alpha as a binary computation offloading decisions. When beta is equal to 1, the task will be implemented locally, no offloading. And when beta is equal to 0 and alpha is equal to 1, the offloading will be to one of neighboring UAVs. And when beta and alpha will both equal to 0, the task will be offloaded and implemented remotely at edge server. Computation model and problem statements. The requirements for each computation task by tuple, data size, CPU cycles, and time concentrate. The computation in all cases, local computation case, nearby computation case, edge computation case, was by calculate the time and energy for each cases as shown in the formulas. The total overhead for processing a computation task in terms of time and energy by summing all cases together and the results in the formula 8 and 9. The computation offloading is formulated as concentrate optimization problem in the equation 10. Our goal is to minimize the weighted sum of energy consumed by the UAV through task offloading distributions. The proposed algorithm is a dynamic programming with Hamming distance algorithm. We used two n cross n tables where n is the number of tasks that need to be completed. The tables are used to store a bit stream to ensure which task needed to be executed locally and which task needed to be offloaded and executed remotely. The generated random bit streams are filled in the first table as ones in the next horizontal cell and zeros in the next vertical cell, so that the first cell always empty. In the second table, the distribution of bit streams will be according to distribution of the first table, and regardless the first bit is 0 or 1. From these tables, we calculate the energy consumption and time of each task. By each cell has ones in the first and zeros in the first table. That means move to second table. From the second table, we calculate the energy and time from the cells that has zeros and 1. Also, we calculate the total energy and total execution time from the tables. In this work, we implemented by using MATLAB program as simulation setup as shown in the table. Number of tasks, 15, data size 10 to 30 10 to 30 megabytes, CPU cycles 1019, 900, and so on. The results. The figure 2, the energy consumption and time execution versus number of UAVs. Where in this work, the UAV can offload the task into 5 nearby UAVs at maximum. As shown in the figure, both energy consumption and time are decreases whenever the number of UAVs increase. Also, in the figure 3, as shown, the energy consumption and time execution are decreasing when the data transmission data rate are increased. The figure 4 and 5. The figure 4 and 5 describes the total time and total energy consumption versus the transmission data rates in local computing, nearby computing, edge computing. As shown in the figures, the total execution time and total energy decreases with increase the transmission data rate. When the UAV has offloaded the task into the edge server or into nearby UAVs, while the energy and time stays constant in case local execution in both cases. The proposed algorithm, it finds an offloading decision according to wireless transmission rate. The figure 6 and 7 are describes the energy consumption and time execution versus the number of tasks in all cases, local and nearby and edge computation, where in all cases the energy consumption and time execution are approximately linearly increase with increase the number of tasks. In case in case edge server execution, both energy consumption and time execution are much less than the energy consumption and time execution in case UAV's execution. This is because the capability of edge server for data processing is much higher than the capability of UAVs. In the conclusion, we proposed a multi-level computation offloading algorithm based on dynamic programming paradigm with randomization and Hamming distance to solve optimization problem. The offloading of the algorithm offloads the task dynamically as possible as to achieve optimal solutions, where the offloading process implements when the bandwidth of the network is high. We conclude that the algorithm reached nearly optimal solutions where the simulation results shows that a minimal energy achieved while meeting time and energy constraints. Thanks for your attention.
Thank you, Abbas. Thank you for your talk
Thank you.
on offloading algorithm, and please ask questions. If no questions, I have a question. As I understand, your heuristic algorithm solves a minimization problem for the total energy consumption within the given constraints on local latency and local energy consumption. And
Yes.
my question is it possible to solve the problem by brute force? What is the computational complexity of this problem? For example, for your numerical example, what is the number of tasks? 15, as I remember, and the number of UAVs was 8 or 10. What is the computational complexity?
The number of UAVs was 10, but the offloading maximum to five nearby UAV. One UAV, for example, UAV 1 can offload the task to maximum five UAV, nearby UAV, or remotely to base station.
So we can get the exact solution for case of 4 or 5 UAV. And have you evaluated the loss of accuracy versus the exact solution? Have you?
Can you repeat, please?
Did you compare your heuristic algorithm and the exact solution? How do we benefit from applying your heuristic, and what are our cons when applying your heuristic? The loss of accuracy, of course. Cons is the loss of accuracy. Am I right? Well, please do some comments on this point.
I don't understand your question.
Okay. So speaking about the exact solution, please. My comment is please evaluate the computational complexity. and then compare the computational complexity of the exact solution and the computational complexity of your heuristic algorithm. Thank you. And more questions, please. If no question, we thank Abbas for the presentation. And this was the last presentation in our session. We are 10 minutes later with the end of the session, but we have heard the interesting talks. Now we have a lunch break, and we will continue with track A at 1:30 p.m. I'm in Moscow time, GMT +3. So I don't say goodbye. See you in 20 minutes. Thank you very much, dear participants. Dear friends, good afternoon. A lot of participants here I see. I'm Yulia Gaidamaka, professor at Applied Probability and Informatics Department of Rudin University. And now we will start the second session of track A. And my co-chairs in these sessions will be Dr. Daria Ostrikova and Dr. Vitaly Beschasny. Daria, Vitaly, are you here? Hello, yes.
Hello, yes, we are.
Yes. Hello, Daria. Hello, Vitaly.
Hello, Yulia Vasilyevna. Yes,
hello.
we're here.
Nice to hear you. Nice to see you. And we also have a technical assistance at track A. Her name is Anastasia Polishuk. Anastasia have helped me with the first session of track A, and she will be with us on track A all day long. And you may ask Anastasia about solving your technical problem. And this is mentioned in our chat. You can see all the names there. And in the second session of track A, we have 8 presentations on the agenda for the coming 2 hours. So I kindly ask the speakers not to exceed a quarter of an hour, including questions. And now I give the chair to Dr. Daria Ostrikova or to Dr. Vitaly Beschasny, who will hold the session. Who will be first, Daria or Vitaly?
I will be first.
Thank you, Daria. Let's check the presenter and let's start.
Yes. You. Hello. Good afternoon, dear colleagues. So, if nobody minds, I think we can start our section. It is my pleasure to be the chair of this section today. And so, by the program, we have 8 talks. And so we have 15 minutes by each talk. And I hope that all presenters are here and we can start our section. So, by the program, the first talk is Amani Sabaf and Maxim Sherbakov, an efficient cluster routing protocol for vehicular ad hoc network using bio-meta-heuristic algorithm. Are presenters here? Who is the presenter?
Yes, hello.
Hello. Yes, we can see you and we can hear you.
Okay.
Can you share your presentation, please? Yes, we can see your presentation.
Good.
So you can start, yes.
Thank you. An efficient cluster routing protocol for vehicle ad hoc network using bio-meta-heuristic algorithm. Outline, introduction, proposed protocol, performance evolution. Motivation of VANET, Intelligent Transportation Systems, ITS, technologies, advanced transportation safety and mobility by integrating advanced communications technologies into transportation infrastructure and into vehicles. Changing over digital age is becoming the driving force for the modern approaches to provide a safe road system. Vehicular ad hoc network is a new network that is used in ITS to enhance the safety of drivers and passengers and to prevent many accidents. It plays a basic role in the ITS. It consists of a group of moving or stationary vehicles connected by a wireless network. VANETs vs MANETs. Mobile ad hoc network MANET is a network of wireless mobile device. VANET is a special class of MANET, but VANET have some features better than MANETs, overcoming the energy constraint limitations and high mobility, but predictable and restricted with the road. Routing protocol in VANET. Routing is one of the most important operations in VANET because it's responsible to data exchange between nodes through wireless channels. The history of routing protocols VANET starts from the traditional routing protocols MANET. For example, OLSR, AODV, DSDV, and DSDV. AODV routing protocol performs better in VANET. An efficient routing technique of data buckets could ensure delivering the warning message during collisions on time, and they also could avoid a large number of accidents. Enhance performance of AODV protocol with the use of clustering and biometa heuristic algorithm with the fitness function. Clustering in VANET. The communication in VANET could be V2V and V2R. There are several techniques available for V2V connectivity optimization. Clustering is an important and effective optimization technique. Clustering is the process of grouping nodes with common attributes with each other into subgroups. The attributes are determined in advance based on the system requirements and the goal to be achieved. In general, the clustering process in VANET can be classified in two types, static and dynamic. Static clustering is based on V2R, where roadside units are the head of clusters. Dynamic clustering is based on V2V, where each cluster is responsible for choose the cluster head from the among cluster nodes according to some important attributes that the head should have. Unfortunately, the traditional routing protocol developed for MANET face many difficulties to meet the constraints and requirements of a complex VANET environment, especially the node mobility pattern, unstable network topology, and the need for timely data transfer in collision avoidance and warning applications. In our proposed protocol, K-means clustering is used for cluster formation, and the cuckoo search algorithm is used for selecting the cluster head. The selecting of cluster head depends on three weighted parameters, distance, angle, and road ID. The weight parameters are used as fitness function along with the cuckoo search algorithm for routing optimization. First, we will start with cluster formation. K-means clustering algorithm has employed since they effectively manage routing problems in ad hoc networks. Because of the swift convergence and easy implementation, they are generally preferred in VANET. K-means algorithm is an important type of flat clustering, aims to reduce the mean squared Euclidean distance from the centers of clusters. The implementation of K-means can as follow. Start initial fixed number of cluster, selection normal centroid, calculate distance, and if the distance is minimum, join this node to cluster or find another cluster. Repeat that until all node has a cluster. This is the pseudocode of cluster formation. Cluster head selection. Cuckoo search algorithm is one of the most important meta-heuristic algorithm. It is developed in 2009 by Xin-Shi Yang. Cuckoo search algorithm is a behavior algorithm which is effective to solve optimization problem based on the behavior of some cuckoo types. The main step of cuckoo search algorithm as follow. initial population of n host nest. Start with iteration 1 and repeat until fixed number of iteration. Choose cuckoo I random by using Levy flight, and then calculate the fitness function for I. Then choose the nest J from the population. Calculate the fitness function of J. If fitness function of I less than fitness function of J, replace J with the I. Or repeat until the find the best node in the cluster. This is the pseudocode of cluster head selection. Then we will explain the weighted function parameters that which used in the cuckoo search algorithm to choose the best cluster head in the cluster. The function consists of 3 parameters: distance for choose the shortest road, and angle to choose the stable road. Distance parameter calculate by using the mean value of the distance between 3 nodes as follow. Weighted road parameter calculate by using class NS3 grid map to get the information of road ID. We can know if the two nodes there are in the same road or not. If in the same road will give 0, different road will give 1. At last, angle parameter calculate the angle between 2 nodes to know if these 2 nodes in the same direction. I mean, if the first node go close to the second node, or it move away from the second node. There are 4 scenarios. If the first node in the front and has the same direction with the second, or if the first node in the behind and the same direction also. The third scenario, if the first node in the front but have different direction, and if the first node in the behind and have the different direction also. Now, proposed pseudocode of proposed protocol start with the source node. This is the case if there is no road in between source and destination. The source node will start with route discovery. It will send route request to the neighbor, and each neighbor will send route request to another until reach to the destination. During this, we will the source node will call the k-means to cluster formation and cluster the all node. In the side of destination node, when the destination node receive route request, it should send route replay to the source. It will call the cuckoo search algorithm to choose the cluster head and send the route replay by cluster head, not as AODP to the previous next hop. It will use the cluster head to send the route replay, and in this case, the source will send data by using the cluster head to destination. Here we use the hello bucket. Consists of position, speed, road ID, heading. This is the identification of vehicle of node. And route request consists of source address, destination address, hop sequence number, and weighted parameters. And route replay consists of destination address, source address, and cluster head. Scenario that we use to evaluate the performance of proposed protocol, we're using network simulator NS3 and to simulate the proposed protocol, and bone motion tool to generate a realistic vehicle traffic scenario. We use Manhattan grid as photo. We evaluate the performance of proposed protocol and compare with the AODV. And estimated network performance metrics such as bucket delivery, average delay, bucket loss rate, overhead throughput, depending on the number of the vehicles. This is the table parameters of simulation. This is there are the result of proposed protocol KMCSA and AODV, bucket delivery rate, bucket lost, overhead, average delay, the throughput. We compare the proposed protocol with another algorithm, anti-clone that is used to enhance AODV, but the enhanced was 1. Another algorithm, AODV clustering, the enhanced was, the developed was 1.9. Our proposed protocol KMCSA developed 5%, 3.4. Develop a new routing protocol KMCSA based on AODV along with k-means and cuckoo search algorithm along with fitness function for choosing the best pace according to the nature of the VANET environment. Using the concept of clustering helps in the case of a large number of nodes in the network. Solve the problem of k-means algorithm that falls in the local optimal using the cuckoo search algorithm. Using the fitness function for choosing the best path according to the nature of the VANET environment, which is distance, road ID, and angel, gives better result than the concept of choose the path based on less number of hops in AODV protocol, because it ignored the environment conditions in VANET such as direction. Some reference. Thank you.
Dr. Amani, thank you very much for a very interesting talk. So, do you have some questions, maybe?
Yes, this is a call to the audience. Please, if you have any questions, do not hesitate to ask them.
Please, any questions from the audience? Yes, Evgeny, please, you can ask the questions.
First of all, do you hear me? First of all, it is very interesting, very pleasant talk, very clear, very deep. But I believe that in slide related to cuckoo search algorithm, there is some misprint or mistake, because it is important when you define Euclidean distance, it should be plus on the root and not minus, which I noticed in this description. I believe that in real computation, you use a correct formula, not this mistake or misprint. This is in description of distance AB. Please, if you wish, you can see there is a root, square root. It is Euclidean distance, yes, exactly here. And here I see minus, but it is better to write another sign, plus, please, plus.
Thank you. Thank you very much.
But of course, this comment does not decrease the quality of this nice talk. I like it very much. Thank you.
Thank you.
Thank you, Professor Levner. Maybe any other questions from the audience?
I think I have a question, and this is regarding the fitness function, which you presented a few slides later. You used some coefficients like H1, H2. How do you define them?
It is choose. I think, do you mean can use like Markov to choose the best of this value? But I put by myself.
They're equal, or maybe there are different.
Yes, it is good. It is a case study to study the good value of this parameter. Can use Markov, I think,
Okay.
but I didn't.
Or I think it's possible even to formalize another optimization problem and to somehow to try to vary these values and to see which of these functions would contribute better results in terms of reliability or the metrics you've studied. Okay, thank you. And another question is regarding the numerical results you have presented. We could observe that this behavior of your algorithm is not linear. In some ways, it's for some number of nodes, it displays a bit better, overcome over the compared results, and in some values the difference is not so huge. How can you explain that?
Maybe I understand that you mean I choose the fitness function with the minimum with the least value. Do you mean this?
I see. No. Can you please send the slide with numerical results? A few graphs in the end of your talk. Yeah, here. Here we see that. Yes, I see. As AODV algorithm displays non-linear behavior, but your algorithm, which is KMCSA, is more linear and more predictable. How can you comment on that?
I don't understand what you mean.
Okay.
This I evaluate the proposed protocol performance by a different number of nodes, like 50, 100, and this is the result, and use Excel to. I don't understand.
No, I mean that, for example, at point 150, we have a great difference between the curves.
How much?
But in some points,
the develop?
Yes, but in some points the difference is quite small.
Of course, it will not be. It is the mean value of the develop, not every at 50 and at 100 in the same develop. It will be different, and if I choose another scenario, the result will be another.
Okay. Okay, thank you.
I calculate the mean of all the value of BDR for proposed protocol.
Okay, I see. Yeah, thank you. Thank you for a good and nice talk. Yes.
Thank you.
Thank you. Let's thank our speaker and let's continue our section. And the second talk is by the same presenter. Yes, Dr. Amani. Yes, could you start, please, your second presentation?
Okay.
Yes, we can see the presentation.
Mm-hmm. Now we will study the case of security in a routing protocol for VANET. We study evaluation of reactive routing protocols performance under malicious attacks in VANET. Outline, introduction, routing protocol in VANET, security, performance evaluation. Introduction, we will repeat again speak about VANET and mobile ad hoc and the role of VANET in ITS. Also speak about the difference between VANET and MANET. There is overcoming the energy constraint, limitations, high mobility but predictable and restricted with the road, strict delay restrictions, frequent interruption of connection. So the routing protocol that is suitable for MANET will not be the best protocol in the VANET because it's a different constraint environment. There are also the routing protocol. The routing protocol in an ad hoc network are divided into three types: proactive, reactive, and hybrid. Proactive is table-driven, reactive is on-demand, and hybrid is the mix between proactive and reactive. We studied the reactive routing protocol. Reactive routing protocols are known as on-demand routing protocols where each node doesn't have information about the entire network topology, but stores only the effective route that is currently used to reach the destinations. This type of protocol depends on performing the process of discovering the path to the destination only, when necessary, thus reducing the load of process of frequent updating of a routing table in the network, but increasing the time required to discover the path between two nodes. The most common reactive routing protocol are AODP, ad hoc on-demand distance vector, and DSR, dynamic source routing. Protocol AODP, it is the most popular reactive routing protocol. It is type of hop-by-hop routing protocol. It isn't necessary for the source node to have complete information about the path to destination node, but rather it only needs to know the next hop in the path and so until the destination is reached. Each node is responsible for making independent and local routing decision based on bucket destination address and their route computation. It performs two types of process: route discovery and route maintenance. It provides unicast, multicast, and broadcast communications. DSR is the most popular reactive routing protocol. It is depends on the concept of source routing, where the route will cache to store will cache in the route request. Therefore, the source node has complete information about the path to destination. AODP just know the next hop. It performs also two types of process: route discovery and route maintenance. From the previous, we can notice that also DSR and AODP belong to the same type of ad hoc, but they have difference. In route discovery, every node in DSR transmits the whole path, unlike node in AODP that send only next hop. Also, the discovered route is being maintained for a period of time and stored in the root cache of node, while in AODB it is kept in the routing table. Now we will speak about security challenges in VANET. Implementation of security system for vehicle ad hoc network is difficult and challenged due to its characteristics such as decentralization, high mobility with frequent disconnection, and using wireless channels for exchanging important and safety information. These characteristics make it suitable for linking between vehicles, but also make it vulnerable to many malicious nodes. Also, the expansion of VANET network to cover the largest possible geographical area and the sharing of the largest number of cars in one network helps attacks to choose any location where radio coverage of one on the nodes is located in order to access the network and work to control it by intercepting messages that are transmitted over the network and redirecting or blocking them. Here some types of attacks in VANET: on availability such as DOS, on confidentiality such as traffic analysis attack, on authentication such as CBEL, such on integrity such as message tampering attack, on non-repudiation such as repudiation attack. This attack causes the link failure between the nodes, and that is will lose it. The network will lose the effectiveness and lack the information that which need to reach to the another node. Here we study only the black hole attack. Black hole attack is the famous attack in MANET. It tries to drop the packet and then forward the packet to the destination. Here. Scenario description, we also use like the previous Manhattan grid to study the vehicle traffic scenario, and NS3 for AODB and DSR. We estimated the performance metric, the packet delivery, average latency, and packet loss, overhead throughput, depending on the number of vehicles. Also, it is the simulation parameters that we used. And here is the result, DSR and AODB. We can notice that and under attacks, this is the number 2, 4, 6, 8, 10. We can notice that the AODB has better performance of DSR under attack. Average delay is the same. Robot. We presented the result of evaluating of reactive routing protocol performance AODB DSR in VANET under attack, black hole attack, to specify the impact of malicious attacks on the network and which routing protocol is more effective when increasing the number of black hole. Simulation results depict that AODB protocol outperforms than DSR protocol when we consider the attack in terms of BDR and overhead. Thank you.
Dr. Amani, thank you very much for your second very interesting presentation. Dear colleagues, do you have some questions? I have one question. Do you plan to work on developing another, maybe heuristic algorithm that will be more reliable and robust against the mentioned type of attacks?
Yes, I work on this case study to make my proposed protocol KMCSA square.
Okay. Thank you for your reply. Thank you.
Yes. Thank you.
Yes, maybe just another question from me. Yes, this is about the simulation parameters. You've put number of attacks Am I right that the number of attacks, this is the number of black holes in the network, or not? Just a couple slides.
Attack.
Yeah.
And the number of nodes?
Yes.
50. 50 number of nodes.
And number of black holes. Yep.
Yes. Number of nodes.
2, 4, and 6. Yes. Number of attacks. You mean this is a number of black holes, or what does it mean?
Number of black hole attack.
Okay, I see. And are they how are they distributed randomly or not?
Black hole attack.
Yeah.
Use a class drop bucket. When node attack received the bucket, drop. Don't forward.
Okay, I see. And where is it located? Where are they located, these black holes, in your model when you simulate this?
Random.
I see. Okay. Thank you.
Thank you very much.
Thank you very much. So let's continue with the next talk. Maybe presenters of this talk are here. The next talk is Vladimir Vishnevsky, Konstantin Voitov.
Voitov. Yes.
Yes. Елизавета Baranova and Vladislav Buzdin. Yes?
Yes, we will present our presentation.
Professor Voitov, you are here, yes? And you are presenter of this talk. So, yes, you can start.
How to include?
Could you please share your presentation, or you have any problems? Yes, we can see your presentation.
Do you see my presentation?
Yes.
The term of our presentation is local hybrid navigation system or desert high altitude platform. First part of this presentation will be reported myself, and the second part will be reported Vladislav Buzdin. In this paper, the author proposed the local hybrid navigation system for the high altitude platform based on the drone with the parameters that are shown in this slide. The weight is 32 kilogram, maximum flight altitude is 100 meters, and the speed of the drone is about 0.4 to 1 meter per second. The proposed navigation system must correspond to the following requirements. The system must be completely autonomous, and it provides autonomous tracking and control of the drone in absence of GPS and GLONASS signals. When the drone leaves the system visible zone, it must scan and space and search for it. The system must provide the stable control of drone's position in presence of interference and noise. The accuracy of determination the angle coordinates is 30 minutes. The accuracy determination of the range is 0.1 meter and altitude above 10 meter while landing 0.05 meter at the altitude below 10 meter. To satisfy these requirements, the author proposed the hybrid navigation system that includes millimeter, and optical subsystems. Here we must say that the different signal message in millimeter domain is used to detect location position at altitude more than 10 meters, and the computer vision methods are used to detect the position location at altitude less than 5 meters. Both these methods are used together to detect location position in the range from 5 meters to 10 meters. For millimeter system, we choose frequency domain 60 GHz as there is strong attention in this range. So the transceiver of this range provides a good signal level at a distance of 100 meters along the antenna radiation, but signal is strongly attenuated in a side direction. The structural millimeters, first of all, transceiver of our subsystem located at the drone, and the receiver is located at the land platform. The scheme of the receiver is typical and presented at this slide. Here it is a very important point is the choice of an antenna system to determination of position location, such as angles and range. Here the antenna should be located on 1 meter side, and they are rotated, turned at a certain angle to increase the accuracy of determination the angle coordinates. This is due to choose section the interval of the characteristics with the greatest steepness of pattern antenna. Next, in this section can be used horn antenna, helical antenna, dielectric antenna, and other. Here we choose helical antenna. The reason of this is the helical antenna has approximately the same pattern width as other antennas, approximately the same gain, but each radiation in circular polarization. This eliminates signal loss when the drone turns in space. Next, we calculate the parameters of this antenna, and the results are present in this slide. You can see this result in the figure presented the patterns of two antennas that turn on the angle 60 degree. How the accuracy of coordinate detection is based on the derivative of the pattern, but not the pattern width. So we calculate the derivation of the function describing the azimuthal antenna pattern on the angle and present to this slide. The calculation results allows us to say that the accuracy of angle is about 60 minutes. The next problem where the calculation of the pattern of our antennas. They're located at the car. Indeed, the car is metal and the antenna is located at the corner of the platform. So this leads to the destruction of the pattern. However, the interstructure is internally symmetrical. Therefore, all patterns are symmetrical about the center of the platform. And in this figure, we show ideal and distorted pattern of the antenna. Then, to increase the accuracy, we propose to use antenna arrays. In our case, these arrays include 4 helical antennas. The pattern for this case presented in this figure. All these calculations show us that accuracy of coordinate determination is about 30 minutes. As for range determination, here we use standard typical receiver. This receiver allows us to obtain the pulse duration about 400 picosecond, and the accuracy of range determination is about 0.1 meter. Next part will be present Vladislav Dudin.
Thank you. Let's move to the part of optical subsystem optical navigation subsystem, and now I would like to talk you about. I would like to say about navigation system is a very extremely extensive area. And in this article, we consider local navigation. We believe that most time of the platform will be in line of sight. From here, we think about methodology, which divide into several subtasks. It's object tracking in difficult weather condition. It's restoring tracking in case of loss of an object. Choice of computing and optical equipment, data transformation and filtering in an automatic control system, and about precision drone landing. But in this article, we talk only object tracking. It's a main part of optical subsystem. We choose 3 main method which we use in our prototype, and this prototype work now. There are SIAM RPM. It's method based of SIAM networks, CSRT, and KCF. In these images, you can see the process, the start process from the left side and end of calculation of the right side for every algorithm. For example, in this case, you can see that DA-SIAM RPN and CSRT show the equal results, but the third algorithm lost a track. loss tracking. But in general, we calculate the statistics, and in the largest part of our dataset, DCCN track objects more effective than other algorithms. And you can see it's of these teeny experiments, but we have a lot of dataset and a lot of data like this. For example, for the later experiment, you can see a graph of occlusion, and which show how algorithms track object on the image. In this slide, you can see frequency of calculation per one frame, and there is a big question for big problem for calculation that the most algorithms which track very effectively have have a minimum FPS for our case. But in general, in our experiments and in our camera, which we have, this FPS like approximately 40 for DCCN RPN. It's a blue graph. It's very effective for our system, and we don't have problems with it. Thank you for your attention. If you have any questions, we will be glad to answer it.
Dear presenters, thank you very much for your presentation and for very interesting approach. Dear colleagues, dear participants, do you have some questions?
I have a question. Yeah.
Yes, please.
If you allow me. Yes. Could you please tell what are the main applications for such systems?
The main application.
What do we need them?
Yes, for our.
The application is very wide.
For our
military.
You can see you mean application for our system include the drone with wider drones or all application?
All applications or subsystems.
Okay, thank you much.
One moment. In the all of cases, we experiment with it and try to test in emergency situation, in military cases, in agriculture, and yes, for 5G and 6G retranslators and other and other applications.
Okay, thank you for your reply. And we have another one question from Professor Levner.
Thank you. I have some practical question. Please, 1 minute. Yes. What is the main difference what is the main difficulty when you compare tethered station and low height drone, which is also stationed on the drone, which is flying not very high. What is the main difficulty? What is the main difference in obtain these coordinates, please?
Our systems focus on wired drones.
What?
We consider desert drones. Desert have altitude platform, and the weight of this system is very big.
We talk about drones which connect to the base station by wire, by physical wire. And it's a big problem for optical navigations and other navigations like beacons and other, because a lot of noise, we have a lot of noise from this wire.
Okay. Okay, thank you.
Thank you for your reply. Maybe any other questions, please? It seems we have no more questions, and we can continue with the next talk. The next talk is by Konstantin Витовтов, Елизавета Baranova, and Vladimir Vishnevsky. Investigation of wireless. Yes.
1 minute. No.
Yes, Professor Витовтов.
Do you see our no.
Do you see our presentation?
No, we can see a presentation.
And now?
No. Now it's great. We can see a presentation. Thank you.
Hello, my name is Елизавета Barabanova, and the topic of my presentation, investigation of wireless hybrid communication system reliability and external influence. One of the most important problems in the implementation of 5G and 6G networks is the development of high-speed wireless communication systems. And one of the main problems of wireless optical and millimeter wave system, which used for these next generation networks, is the low stability of the communication channel in relation to the influence of atmospheric phenomena. To solve this problem, different hybrid systems have recently developed, including either optical and millimeter communication channels, or optical and radio frequency channels, or millimeter and radio frequency channels. In this paper, we consider a hybrid system consisting of two data transmission channels. The first one is a high-speed optical channel, which is the main one, and the other a millimeter channel, which is in cold reserve. The case when random interferences lead to a disruption of optical channel operation is considered in this paper. Let us consider the states of the system. The first state is the state when the optical channel is working. The second state is the state when the system is in the mode of switching from the optical to millimeter channel. You can see the third state is the state when the millimeter channel is working, the third state. And the fourth state is the state when the system is in the mode of switching from the millimeter to the optical channel. The time the system is in each of the states is a random variable having an exponential distribution. The intensities of transition from one state to another, lambda ij, in general case are piecewise constant function determined both by the climatic condition of the system operation and its technical characteristics. In this paper, we use the calculation method based on fundamental metrics of the Kolmogorov system. Here you can see, at first we can write the following system of Kolmogorov equation in matrix form. The formula 1. Here P is the state of vector of the system, T is the transposition operator, and A is piecewise constant matrix of the equation Kolmogorov partition. To study the behavior of the system in this work, as I can say, the method of the fundamental matrix of the Kolmogorov equation is used. The fundamental matrix of the system of linear homogeneous differential equation allows one to obtain solution of the system at an arbitrary moment of time for given initial condition. Here you can see the probability of the system state at an arbitrary time instant t, the formula third, and with this probability at the initial time t0. If the transition probability change in a jump at a certain moment of time, then the fundamental matrix after the jump occurs as a matrix of the first interval at the time value equal to the duration of the interval to the fundamental matrix of the center interval. As you can see, at the formula here. And in the presence of several jumps, the behavior of the system on the ith interval is described by the matrix 5. Let us consider the state when probability of state in the absence of jumps in transition instances. So lambda are constant. In this case, the elements of the fundamental matrix M of the equation Kolmogorov system can be calculated using formula 6. And here you can see the element of these elements. One of the main problem of our paper is calculating the reliability indicators, such as reliability factor and downtime ratio. The expression for this indicator you can see in the slide 8 and 9. Also, we calculate the throughput of the system using the maximum throughputs of the optical and millimeter channels and probabilities of states P1 and P3. The next case is the case when probability of states change in the presence of jumps of the transition instances caused by noises. In this the figure, you can see the change of impedances lambda ei, ij, and you can see the formula 12 for three intervals, the first, the second, and the third here. And the formula 13 is a formula for calculating the fundamental matrix when we have n jumps of transition impedances. Using previous formulas, we can calculate the availability factor and the probability of failure. Also, we can calculate the throughput of the system using this formula. The next section is the numerical simulation, and here we have several cases. The first is a simulation of system operation in the normal mode. The result you can see in figure end A and B. You can see the dependence of the hybrid system state on time when the station is turned on. Here on figure C, you can see the case when lambda I 1 and second 0.22125 and 0.00075, and you can see that the probability of the optical channel operating is 0.287. The probability of millimeter channel operating is 0.71. Here you can see on figure A and B, P1 is the probability of the optical channel operating, P3 is the probability of the radio channel operating, and P2 plus P4 is the probability that the system is in the switching mode or there is no connection. On the figure B, the analysis of transient behavior of the system in the initial moment of time on a larger scale. The second case, we investigated the operation of the hybrid station with channel faults. The figure A and B is the cases for millimeter channel failure, and CD when optical channel is failure. The solid line corresponds to the probability that the optical channel is operating, and the dashed dot line corresponds to the probability that the millimeter wave channel is operating. The dotted line indicates that the system is inoperative. Figure C and D show that transit mode. B and D show the transit mode on a larger scale. Note that the downtime ratio of the hybrid station sharply increases in a transit mode. In the event of a millimeter channel failure, its maximum value is 2.25, and in the event of an optical channel failure is 0.145. The next case, when consider the simulation of a hybrid system under the man-made radio influence. You can see the dependencies of the state probability in the event of man-made radio influence to optical channel from the moment of time 3000 seconds. Uh, you can see this case in figure A and B. And for millimeter channel, you can see the results in figure C and D. The availability factor of the optical channel in this case decreases to 0, and the availability factor of the millimeter channel increases to 0.999, and the station downtime factor is 0.001. The dependencies of state probability of the system in event of the man-made radio influences on millimeter channel, you can see in figure C and D. In this case, the noises on the millimeter channel are acting for 5 seconds and finishing for 10 seconds and have 5 periods. On this figure, you can see the state probability of the system under the man-made radio influences on both channels. In figure A, the dashed line corresponds to the availability of the optical channel. The dashed dot line corresponds to the availability of the millimeter wave channel, and the solid line corresponds to the availability of the total hybrid system. The dependence of the downtime radio is shown on figure B, and you can see the maximum value is 0.443 during the time when the noise is active. With a decrease in the interval between the noises, the system does not have time to restore it. The case when the interval between the noise are 1 second is considered in C and D figures. As you can see, the availability factor does not exceed 0.725, and on average, here values this interval, and average is 0.64. So in this paper, we consider the hybrid communication system, including optical and millimeter communication channel, and we use a correct analytical method to calculate the state probability of the system, the availability factor, and the downtime factor, both in stationary and transit mode. And also we consider the influence of noises on the state of the system. Thank you for your attention. Your questions?
Елизавета, thank you very much for your presentation. Please, any questions from the audience?
I think I have a question. Zeta, could you please tell what is the nature of your transient intensities, which are the lambdas? What do they reflect? Maybe what the conditions or interferences, or maybe noise, as you described?
We use values which have been atmosphere interferences, man-made noises, and other is more influence. Just the first atmosphere.
First of all, we consider the influence of atmosphere noise and man-made. Okay.
Okay. Yeah, that's clear. Thank you very much.
Thank you.
Maybe another question. Yes, could you please present the slide with the states of your system?
Okay. One moment.
This one.
Yeah. Thank you very much. Yeah, I see that states 2 and 4 are switching time. Yep. I mean, this the switching, and when do the failures occur?
The failures occur in the state 2 and 4.
So you consider them as failures? Yeah. Okay.
When
I see.
failures occur, the system transmit in the state from the first to the second.
And from the third
From
to the fourth.
to millimeter, and there is the state when the system is in switching state, when there is no any communication, and here in this state the system is in failure state. It is not working in 2 and 4 states.
Okay, thank you. That's clear.
Thank you. Maybe any other questions? Okay, let's thank our presenter. Thank you, Elizaveta. And let's continue our session with the next talk. It seems that this is the last talk. Alexander Grebeshkov, ontology-based model for sensor network fault management. Alexander, are you here?
Yeah, I'm here. And is the translation of my picture and voice, please?
We can hear you, but we can't see your presentation.
Just a moment.
Okay.
Yeah. Is there a picture on the screen?
Just a moment. Yeah.
Just a moment, yes.
Yeah. And dear colleagues, I've got to begin my presentation, and I hope that you have a screen of my presentation this moment, but just a moment. I think that I'm afraid that we have a bit problem with translation. Just a moment. I will try to. Yes.
No, also we see your presentation.
Yes. Okay, and I've got to begin. So I wish to present short report with topic ontology-based model for sensor network fault management, and I'd wish to say some primary words about fact that modern sensor network is extremely different from the point of view not researchers but manufacturers. So we have to if we want to have an artificial intelligence method for management at a sensor network, we have to introduce some common semantic context for this control. So some problem statement you can see on the slide number 2, and I hope that you can see you can see this slide, because we have I have a bit problems with translation. I'm sorry. So, and next slide is number 3. What's the decision for the problem of introducing artificial intelligence for sensor network management? We think that the use of ontology-based method is one of the best solution in this sphere, because ontology-based method help for us to understand a common semantic of our objects, and with the common semantic we will have a chance to understand different data from different type of devices. So you see that the focus of our interest is to make a smart classification of fault events on the heterogeneous type of sensor network devices. And as example, we have a simple technical model. Technical functional model. You can see this model on the slide number 4. You see that typically we have a sensor node as a data source for another applications. Between sensor node we have some communication nodes, backward network, and finally we have special fault processing system, control system, which help for us to make a difference between primary and secondary faults. I'd wish to some short remark about primary fault. Primary fault, it's first fault in the range of faults between source of data and between the user of the data. Because, for example, if we have a problem with actuator or we have a problem with sensor, since we have not got any data for application on the server on the user application. So you see that we can to make some functional blocks as ontology-based classifier for the devices of sensor networks. And the next we have a special, we think that it will be interesting for you. We have a supervised learning model for fault classification. So, and from the ontology-based point of view, we have a scheme on the slide number 5, and you see that our model have some blocks. For example, this block sensor node, it means description of sensor node class, and the gateway block is it means a description of gateway classes. So we have that in the focus of our model is a fault event, and this fault event has connections with another part of this scheme, and with predicate calculations we have a chance to introduce this model as a large a set of logical formulas. For example, we have these logical formulas on the slide number 6. And you see that in this formula we have a sensor node, gateway, and the radio channel, and so on, and these all type of devices which we have in our scheme. Next is a description of connections between all these all these classes, and the fault event, and we have a description of part of scheme on the slide 5 which can be affected by fault event. So we have that sensor node, gate, channel, wireless sensor network, so on and so on. They can be subject of affected from the fault event. And the last but not least, definitely, but not least part of this rule is the logical logical expression, which shows that if we have status node fault for example, wireless sensor network, communication node, and the network, since the source of the primary fault was sensor node, you see. Definitely, this type of notation is not. I think that this type of notation for this day is not well known for all specialists. But for example, it's the typical. It's the typical formula. For example, if we have, if we deal with the ontology-based model. And the last, but the last of our idea is to integrate ontology-based model with a supervised learning model. For example, for decision for finding decision in the field of classifier. And so I think that with the model, with the algorithm on the slide number 7, we'll have a chance to understand which kind of type of devices on the slide number 5 and 6 was a primary had a primary fault message, and which kind of device on the slide 5 and 6 has a secondary message about fault. So now we will have some ideas about integration. For example, ontology fault model with a supervised learning model. And I think that when we will have a lot of statistics from a fault event at the sensor network, we will have we will produce good results in this field. And thank you for your attention. And I'm so sorry for problems with the communication. So. And I've got to answer for a question. Thank you.
Thank you very, very much for your very interesting presentation. Dear colleagues, dear participants, maybe you have do you have some questions?
And yes, Professor Kibishkov, yeah, I have maybe first of all, thank you for your talk. Yes, and the connection was good and everything went fine.
It's right.
So, yes. So yeah, and the question is, what your approach allow for example, machine learning techniques that you use? What they are targeted at? What is the goal of these techniques to represent the priorities of the faults to the user, or maybe?
Okay, and for these days, we are in the start of the machine learning process, studying. We have not got for these days another experience in this field, but I see I wish to talk that I think the main focus of our work is to make some products, to make some methods for predictive management. So I can at this moment, I can recognize the thing that, for example, we have not got ideas about how to make a forecasting for example, about wireless sensor network function for a short time period. And I have that when we'll have our integration method with the fault-based ontology-based classification, and when we will have as supply method as supervised machine learning, we'll have, for example, first of all, we will have a good classifier between a primary and secondary fault. And first and then second, I think that will make some models for the future, for example, for short time period in the field of differences between forecasting of primary fault and forecasting of secondary fault.
I think thank you so much. Yeah, that's
thank
clear.
you for you.
Thank you. Maybe any other questions?
Okay. Okay. Thank you, Professor Kubishkov. Yes, for your interesting talk.
Отлично видно, да. Ну хорошо, тогда, поскольку уже время начала работы секции уже идет, время работы секции уже идет, я начну с первого доклада. Так получилось, что доклад, вот я тут участник, еще несколько моих сотрудников, и аспирантов, которые участвовали в подготовке этого доклада. Но так получилось, что почти все тут они оказались занятыми. Кто в командировке, кто отъехал, и придется, значит, выступать мне. Ну, доклад называется, ну, по-английски здесь написано, все вы видите, я его не буду озвучивать. Ну, насколько я понимаю, у меня слайды подготовлены на английском языке, ну, говорить я буду по-русски. Ну, если есть вопросы на английском языке, на русском языке я готов ответить. О чем пойдет речь в докладе? Значит, в докладе рассматривается возможность улучшения работы, использования концепции network slicing при обслуживании гетерогенного трафика. Ну, из истории телекоммуникаций нам известно, что раньше...
Николай, попроси всех отключить микрофоны. Там кто-то оставил включенный микрофон и слушает другую всех.
Микрофон? У меня тут нет ничего.
Всех выключить микрофоны присутствующих.
Присутствующим просьба выключить?
Конечно, потому что слышно их там переговоры.
Ну понятно. Хорошо.
Константин Евгеньевич, у всех выключено.
А что это за звуки, Антон?
Так, я сейчас говорю, нормально мне слышно?
Это у Сергея Николаевича какие-то со звуком.
У меня со звуком? А что у меня может? У меня тут вроде ничего
Местами
нет.
пропадаете.
Местами я пропадаю? Так. Ну, а сейчас я лучше, я стал чуть погромче говорить.
Я слышу,
в целом удовлетворительно,
на фоне идет, какие-то голоса идут на фоне этого.
Голоса? Не, ну у меня тут я сижу один, с автором рядом со мной нет. Не знаю откуда. Ну, хорошо, давайте я продолжу.
Нет, все прошло, все нормально.
Нормально, да? Ну, я продолжу. В общем, так, исторически развитие телекоммуникаций складывалось в соответствии с таким утверждением. Если мы обслуживаем много потоков, то лучше эти потоки обслуживать общим ресурсом. В этом случае у нас потери будут меньше, и использование единицы ресурса будет больше. Если потоки заявок, которые поступают однородные, то есть это заявки на предоставление одного определенного вида сервиса, это действительно так. Это можно показать математически, если, ну, например, в рамках модели Erlang рассматривать. Там действительно потери заявок падают, а использование единицы ресурса растет. Но ситуация сейчас меняется. Узлы доступа обслуживают мультисервисный трафик. И в этом случае у нас возникает конкуренция поступающих заявок за свободный ресурс.
И вот эта конкуренция приводит к тому, что заявки, ну, например, заявки, которые требуют объем ресурса не очень большой по сравнению с заявками других потоков, которые требуют большой ресурс, они могут просто вытеснить из обслуживания вот эти тяжелые заявки, так называемые. И вот здесь вот численный пример приведен небольшой. 3 потока, 200 единиц ресурса, и обслуживаются заявки с требованиями 1 канал, 10 каналов, 20 каналов. И вот мы видим, что здесь на левом рисунке показана доля потерянных заявок, на правом среднее число занятых единиц ресурса. Вот поток номер 1 – это поток, который требует меньше всех ресурсов, поток номер 3, который требует больше всех ресурсов. И мы видим, что с ростом, ну уже при сравнительно небольших значениях нагрузки, там порядка до единицы на 1 канал, у нас уже происходит такая ну, мы видим, что качество обслуживания начинает сильно зависеть от того, сколько ресурсов требуется заявкам. Чем меньше ресурсов, тем качество лучше, чем больше ресурсов, тем качество хуже. И вот особенно ярко это проявляется в ситуации перегрузки. В этом случае легкий трафик у нас просто может вытеснить из обслуживания трафик, который тяжелее его. Вот мы видим, заявки потока 2-3 просто уходят с обслуживания, никакой ресурс не занимает. Когда потери маленькие, они занимают, как вот видно здесь на рисунке, одинаковый ресурс. Так были подобраны параметры, что предложенная нагрузка у них одинакова, общая. Но вот с ростом нагрузки на канал начинает возникать такая дифференциация. Ну, с этим надо как-то бороться. Дифференцированное обслуживание, то есть обслуживание, которое связано с тем, чтобы мы предоставляли какое-то гарантированное качество каждому потоку заявок, привело вот к реализации концепции network slicing. Network slicing поступает наоборот. Мы не будем объединять все потоки заявок на общем ресурсе, а каждому выдадим потоку или группе потоков с примерно одинаковыми требованиями, мы выделим свой ресурс, слайс, и он будет на этом слайсе обслуживаться, и мы будем в этом ситуации мы можем подсчитать объем слайса так, чтобы потери заявок и занятые ресурсы у них были теми, которые требовались. Применение этой концепции, оно основано вот на таких модных терминах, как SDN, Software Defined Networking, Network Function Virtualization и так далее. Вот эти инструменты дают нам возможность создавать платформу для выделения слайсов поступающим потоком заявок. Ну, тут же, как бы, раз есть инструменты, надо предложить сценарий их использования. Ну, вот самый простой сценарий, вот, который на этом слайде реализован, это просто статичное распределение ресурса. Каждому потоку или опять-таки группе потоков с одинаковыми условиями обслуживания выделяется слайс, ну и дальше поступающие заявки этот слайс используют для получения сервиса. Ну, тут сразу, когда есть некий сценарий, начинаешь думать о том, какие у него позитивные, положительные характеристики, какие отрицательные. Ну, вот положительными характеристиками статичных сценариев, ну, следующие, вот тут 3 у меня приведены. Ну, во-первых, процедура конфигурации, ну, то есть процедура планирования слайсов очень легкая. Потому что мы фактически решаем задачу определения ресурса для моносервисного трафика. И задача давно решена. Второй положительный момент связан с тем, что изолируя потоки заявок, изолируя информационные потоки с разными требованиями, мы как бы предохраняем их еще от возможных проблем, связанных с потерями, там, с безопасностью, с перегрузкой, ну и так далее. Ну, на эту тему я пока говорить не буду, но вот это тоже позитивное качество статичных сценариев. Ну и, наконец, ну вот я уже отчасти упомянул, статичная локация ресурса, она очень легко, ну, сравнительно легко анализируется математически. Ну и отрицательные характеристики статичного сценария тоже легко предсказать. Здесь как раз отрицательной характеристикой является неэффективное использование ресурса, который резервируется в слайсе. Значит, этот ресурс нельзя быстро передать в другие слайсы, если там возникла некая необходимость в дополнительном ресурсе передачи информации. Ну вот теперь, когда стали понятны положительные и отрицательные моменты этих сценариев, ну, тут же возникло желание сочетать позитивные характеристики статичных сценариев и динамичных сценариев. Ну, динамичным сценарием я здесь называю сценарий, когда все информационные потоки обслуживаются на общем ресурсе. Там нет деления на слайсе. Когда мы пускаем все в общую трубу, у нас, вот, несмотря на то, что потери заявок могут сильно различаться между собой, и какие-то заявки могут вытесняться, тем не менее, в большинстве случаев использование единицы ресурса достигает максимальных значений. Ну вот, как бы надо построить сценарий, который находится посредине между статичным и динамичным. И вот эти сценарии, группа таких сценариев, она построена на принципе ограниченного доступа. Мы будем ограничивать доступ для части заявок, которые как бы у нас вредят процессу обслуживания, совместному процессу обслуживания гетерогенного трафика, и давать преимущество другим потокам заявок. Ну, здесь вот как бы реализуется какая идея? Давайте мы часть нагрузки дадим, значит, одному потоку и выделим часть ресурса, дадим потоку, поступающему заявок, а часть ресурса сделаем общим. Это будет такой буфер, который будет использоваться для того, в той ситуации, когда у нас там всплеск нагрузки происходит или требуется повысить эффективность использования единицы ресурса. Здесь, конечно, процесс математического анализа, так сказать, усложняется, поскольку потоков много, и у них есть некая дисциплина занятия ресурса, но, тем не менее, значит, ну, и видно какой-то позитив. Позитив связан с тем, что мы можем экономить ресурс при таком интеллектуальном его распределении. Ну, значит, необходимость математического анализа таких сценариев связана еще с тем, что, в принципе, вот эти инструменты, они не прописаны в стандартах ETC. И, значит, каждый оператор или вендор должен пытаться сам их разрабатывать. И поэтому математический анализ необходим. Так, ну теперь давайте, ну, чтобы быть как-то определенным, дальше будет рассматриваться, ну, такой сценарий работы оператора, который, ну, собирает данные с датчиков, камер и так далее, и пытается их, значит, обслужить на каком-то ресурсе беспроводной связи, узел. Ну, это может быть даже узел LTE или узел доступа каких-то технологий более далеких. Ну, то есть у нас есть очень гетерогенный трафик, есть ресурс, есть возможность его как-то этим ресурсом манипулировать. Предположения, какие, значит, сделаны. Ну, вот здесь вот для того, чтобы дать приоритет в обслуживании какому-то виду трафика, мы будем использовать так называемую фильтрацию. То есть мы будем пускать заявки к ресурсу, ориентируясь на общий уровень занятости ресурса. Значит, это один из способов фильтрации. Можно думать то есть можно пускать заявку, глядя на то, какой ресурс занимает заявки данного потока, это, значит, такие модели с ограниченным доступом, а можно смотреть, ограничивать доступ, исходя из общего уровня занятого ресурса. Вот здесь рассматривается именно этот принцип. Ну и, значит, мы рассмотрим два сценария. Network slicing, когда ресурс делится между поступающими потоками, и вот фильтринг, это, значит, когда у нас доступ заявок к ресурсу ограничен и зависит от общего объема ресурса, занятыми всеми потоками. Ну, модель выглядит вот таким образом. Значит, мы считаем, что у нас есть n произвольное число заявок. потоков заявок, все потоки пласоновские. Будем говорить о том, что поступающие заявки связаны с сервисами реального времени. Известна интенсивность поступления заявок. Для первого, для катового потока это лямбда К, требования к ресурсу БК каналов или там БК виртуальных каналов требуется для обслуживания поступающей заявки. И время обслуживания также имеет экспоненциальное распределение с параметром μk. Теперь, когда заявка катового потока поступает, она принимается к обслуживанию с вероятностью единицы минус φKi, где φKi некая вероятностная функция, меняется от 0 до единицы, а и общее число занятых единиц ресурса вот в нашем общем пуле, который мы рассматриваем. Он состоит из V-каналов. Вот здесь вот эти все те предположения, о которых я говорил, они сформулированы. Дальше некое такое стандартное исследование. Модель описывается мерным марковским процессом. Значит, ИК – число заявок катового потока, которые находятся на обслуживании в момент времени T. Пространство состояний у нас И1 и N, где ИК – число заявок катового потока, находящихся на обслуживании. Но мы не можем, не зная конкретный вид функции фильтрации, не можем конкретно написать ограничения на те состояния, которые в наше пространство входят. Понятно, что они должны удовлетворять вот этому неравенству, но дальнейшие ограничения связаны с конкретным выбором функции фильтрации. Дальше, поскольку марковский процесс, мы можем составить и решить систему уравнения равновесия и определить характеристики, зная вероятность отдельных состояний. Значит, характеристики записываются в виде... Да, тут, кстати, опечатка здесь не единица минус FKI, а FKI. Значит, это доля потерянных заявок, и обслуженный ресурс. Система уравнения равновесия стандартным образом выписывается, выглядит вот так, как здесь представлено. Она записана в виде одного соотношения. Да, я еще хотел сказать, что тут, поскольку мы ввели вот эту фильтрацию, то мы из-за нее потеряли такие хорошие свойства, которые у некоторых моделей мультисервисных узлов наблюдаются. Это обратимость. Отсюда у нас не получается точных рекурсивных алгоритмов, которые могли бы использоваться для оценки характеристик. Поэтому, если точно надо рассчитать, приходится составлять и решать систему уравнения равновесия. В данном случае итерационным методом Гаусса-Зейделя. Это очень удобно делать до нескольких миллионов состояний. Можно использовать и приближенные подходы. Приближенный метод здесь как раз основан на том, что мы предполагаем обратимость, свойство обратимости этого процесса. И из этого предположения вытекает вот такое равенство, которое здесь представлено. И это равенство, оно нам дает возможность получить рекурсию. Рекурсия, она похожа на ту рекурсию, которая для мультисервисной модели Erlang используется, рекурсия Кауфмана-Робертса. Она выглядит таким образом. Этот подход очень точный, погрешность там часто бывает в пределах нескольких процентов, и он может использоваться для оценки характеристик. Так, теперь давайте посмотрим, применим вот эту фильтрацию и сравним ее просто со статичными сценариями. То есть у нас есть, чтобы упростить картинки, давайте мы предположим, что у нас всего два потока есть трафика, тяжелый и легкий. То есть у нас есть заявки, которые требуют мало ресурса и много ресурса. В принципе, все дальнейшие рассуждения, о которых идет речь дальше, их можно отнести и к мультисервисному трафику, когда у нас не два потока, а больше. Мы опять-таки можем сгруппировать потоки в легкую, во множество с легкими требованиями и с тяжелыми требованиями и рассматривать их как группу из двух групп. Либо просто более сложные картинки рисовать, там просто требуется больше вычислений. Какие задачи? Посмотрим. Три задачи такие здесь сформулированы. Первая задача состоит в следующем. Нам дан ресурс общий V каналов. И надо найти разделение ресурса на отдельные слайсы, которые делают равными потери для обоих потоков. Вторая задача, как бы развитие первой задачи, она состоит в том, что надо, мы используем не готовый там объем ресурса, а мы должны найти объем ресурса такой, чтобы и разделить этот ресурс на части так, чтобы у нас потери были равны и, значит, достигали заданного уровня, вот заданного уровня π. Ну и третья формулировка на развитие второй, и она, значит, заключается в том, что мы должны найти общий объем ресурса, должны его разделить на слайсы так, чтобы потери заявок первого потока были на уровне P1 со звездочкой, а второго на уровне P2 со звездочкой. То есть мы как бы здесь полностью реализуем принцип дифференцированного обслуживания. Заявки должны получить те потери, которые как бы заказаны. Ну, вот здесь показано решение задачи вот для тех параметров, которые здесь представлены. 200 каналов, 2 потока, требования к ресурсу 1,10, ну и потенциальное число соединений 100, для первом случае 10 во втором. Ну, тут параметры подобраны так, что у них предложенная нагрузка одинаковая в канальных единицах, она равна по 100. Ну и вот здесь вот несложно методом просто перебора получить для статичного сценария, что решение достигается, если мы в первом слайде сделаем 88 каналов, и при этом общие потери будут 0,161 тысячная. Вторая задача. Вторая задача, мы должны уже найти число каналов и опять разбить эти каналы на слайсы так, чтобы потери были равны и равны примерно по 0,05. Ну, вот опять-таки, меняя величину V1, объем слайса, мы решаем эту задачу и находим, что для этого достаточно взять 255 каналов и разбить вот в пропорции 105 и 150. Потери будут 0,05. Ну, третья задача. Здесь, значит, опять 2 потока, те же требования к ресурсу, тот же предложенный трафик. И, значит, надо сделать так, чтобы потери первого потока были 0,01, а второго 0,001. Ну и вот опять-таки, меняя величину слайса одного, мы подбираем вот эти величины слайсов. Да? Значит, 117 у нас будет в первом слайсе, 210 во втором, и потери будут вот те, которые здесь были заказаны. 0,01 и 0,01 и 1 тысячная. Так, это вот мы решили нашу задачу с помощью статичного, в рамках реализации статичного сценария. Следующая часть, значит, исследования связана с решением этих задач с помощью фильтрации поступающих заявок. Опять берем тот же самый пример и, значит, вводим функцию фильтрации, которая будет у нас ограничивать доступ легких заявок. Значит, здесь вот величина R1, это как раз дополнительное резервирование, которое, значит, R1 это то число каналов, которые как бы резервируются в пользу тяжелого трафика. Легкий трафик их занимать не может, хотя мог бы и сделать это. Ну, давайте смотрим. Значит, решение первой задачи, оно получено, ну, значит, здесь вот R1 найдено, то есть уровень резервирования, который надо использовать, и ответ. Ответ, значит, здесь достигнут, то есть мы выравниваем потери заявок и выравниваем их на уровне 0,142 на том же объеме ресурса. То есть если мы сравним с решением, которое ранее получено, это решение лучше, потому что здесь были потери 16%, а здесь у нас потери 14%. Ну, 2% тоже это выигрыш. Вторая задача, мы должны подобрать общий объем ресурса и опять предоставить вот заказанное обслуживание для первого и второго потока. Значит, заказанное обслуживание, это значит потери заявок первого потока и второго должны быть 5%. Вот решение достигнуто при общем объеме ресурса 238. Ну, сравниваем с тем, что было раньше. Значит, здесь 255. То есть мы выиграли, ну, там, порядка 20 каналов. Это уже 10% от общего объема ресурса. Третья задача, Вот теперь третья задача. Да. Мы теперь должны опять найти общий объем ресурса и предоставить заявкам первого потока качество обслуживания на уровне 1%, второго потока на уровне 0,1%. Здесь ответ тоже получается вот при выборе вот уровня резервирования 24, и ответ такой: 297 каналов. И опять этот ответ лучше, чем тот, что был получен здесь. Здесь 327, там мы получили 297. То есть мы видим, что вот эта фильтрация, она дает нам возможность получить решение на меньшем количестве, на меньшем объеме ресурса. Это означает также, что у нас ресурс лучше занят. Ну, вот эти примеры я здесь не привожу, времени мало. Ну, так что мы показали, что фильтрация, вот возможность такого гибридного занятия ресурса, когда мы что-то отдаем, а что-то делим, а что-то используем в общем доступе, она дает возможность экономить нам. Так, ну и еще один момент, связанный с преимуществом таких вот комбинированных сценариев, это вот устойчивость к перегрузке. Ну, чтобы ее показать, давайте мы возьмем два решения, которые были получены при статичном сценарии и при фильтрации. Вот статичный сценарий, вот здесь мы получили 327 каналов, и этот 327 каналов обеспечивает нам вот эти потери, которые здесь были получены. Да? А теперь возьмем тот же самый результат, полученный с помощью фильтрации. Да, значит, это вот это решение, а с помощью фильтрации мы получили вот это решение. Ну и теперь давайте устроим перегрузку, да, сымитируем перегрузку. Будем увеличивать интенсивность потока заявок, интенсивность первого потока заявок там в определенных пределах, и посмотрим, как будут меняться потери заявок первого потока и объем занятого ресурса. Не объем занятого, а среднее использование ресурса. И вот эти картинки, вот эти картинки показывают, что произойдет. Вот слайсинг это вот network слайсинг, когда мы используем статичное использование ресурса. А фильтринг это вот когда мы просеиваем заявки. Мы видим, что здесь потери, то есть у нас сильно нарастет нагрузка, она увеличится там, от 100 Erlang до 200. Ну и здесь вот мы при слайсинге потери у нас растут больше 40%, а здесь они только до 20% выросли. Среднее использование ресурса здесь оно тоже, здесь оно вообще у нас будет ограничено, поскольку слайсинг он не дает нам избытка ресурса. А здесь мы, видите, можем забраться довольно высоко, то есть больше 85%. Ну это тоже еще один позитив такого предложенного подхода. Ну, значит, здесь выводы приведены, ну, я их уже там частично озвучил. Значит, ну, построено некий подход к такому гибридному использованию ресурса, который дает возможность реализовать дифференцированное обслуживание поступающих заявок и выбрать те характеристики качества обслуживания, которые заказаны на общем объеме ресурса, используя его ограниченный доступ с помощью фильтрации. Ну вот, на этом я заканчиваю. Если есть какие-то вопросы, я готов ответить.
Ага, Сергей Николаевич, вы же сам председатель и есть, то есть можно уже реагировать на ваше предложение, задавать вопросы, я поняла.
Да, я такой, как мультисервисный человек.
Спасибо большое за очень интересный доклад. Мы всегда с огромным удовольствием смотрим за вашими результатами и прям знакомые странички из вашей книги, из обеих ваших книг, которые у нас стоят на полке на кафедре. Наши студенты с ними знакомы. И очень интересно было услышать ваш подход к нетворк-слайсингу. Мы, правда, немножко по-другому называем нетворк-слайсинг, определяем его, но это вы сегодня послушаете еще на вашей секции, будут два наших аспиранта выступать. Ваш фильтринг, вот именно его мы скорее называем нетворк-слайсингом. А вопрос у меня такой. Скажите, пожалуйста, когда мы выписываем функцию фи kt от i, откуда мы берем значение и, начиная с которого мы начинаем просеивать поток. Ведь эту константу нам должен задать заказчик, оператор, правильно я понимаю?
Не, ну вот дело в том, что здесь заказчик нам ничего не дает, мы эту ситуацию моделируем заранее. То есть это мы даем возможность как бы предвосхитить то, что произойдет. В рамках модели мы это и знаем. Поэтому мы моделируем и говорим, вот если мы будем резервировать на таком-то уровне, то мы получим ответ.
А вот тогда вопрос на засыпку, что называется. А можем ли мы так сформулировать задачу в рамках вашей модели, чтобы подбирать вот этот порог, начиная с которого мы перестаем пускать заявки в систему? Потому что вот именно в такой формулировке задачу решают наши аспиранты. Подобрать порог.
Подобрать порог, ну правильно, здесь же порог тоже подбирается. Вот когда мы видели здесь, вот я показывал графики, там внизу вот R1, эти кривые, они шли в зависимости от R1. R1 это и есть порог. R1 это число каналов, которые резервируются в пользу там какого-то вида трафика. Поэтому они подбираются, да.
Ага, спасибо. А теперь, можем ли мы сформулировать задачу оптимизации, чтобы какой-то показатель мы пытались найти решение, так подобрать пороги, чтобы максимизировать или минимизировать там заданный показатель? Вот так еще не пробовали вы формулировать задачу?
Нет, я вот тут как бы я старался, поскольку дифференцированное обслуживание, оно предполагает там как бы достижение заданным потоком заданных характеристик, да, вот как бы задача ставилась так. Ну, можно построить там какой-то функционал, он все равно будет зависеть от использования ресурса, от потерь и так далее, и возиться с этим. То есть я вот как бы в таком виде работаю с характеристиками, но не связываю их с экономикой. Может быть, это как бы и надо делать.
Да, все верно, экономика ни при чем здесь. Правильно.
Я еще хотел сказать, что вот подходов вот к такому комбинированию довольно много. Вот это, вот, скажем, постановка, она родилась у меня вот после того, как я ознакомился с диссертацией Бегишева и там вот Петрова, статьи их там читал. Там тоже была вот реализация, там слайсинг он, может быть, не назывался, но как бы тоже совместное использование ресурса несколькими потоками заявок, и мы просто можем как бы делить ресурс статично, а можем его делить так, вот тебе столько-то дадим, а какую-то часть мы будем использовать сообща. Ну и вот, просто вот эту задачу можно по-разному решать. Вот эту, можно ограничивать доступ, исходя из ресурса, занятого определенным потоком, или исходя из того ресурса, который занят всеми потоками. Можно просто жестко выделить там какое-то число, сделать вот эту общую часть переменной, ну и построить такое вот как бы неполнодоступное включение. То, что раньше, кстати, делалось давно-давно, когда систему междугородней связи рассматривали. Там каналы, они потом объединялись. Вот у нас было такое вот, то есть подходов довольно много есть.
Спасибо, Сергей Николаевич. Спасибо, да. Ну вот у Бегишева действительно там не network slicing в современном понимании, так как в стандартах он определяется, международных телекоммуникационных. В телекоммуникационных стандартах слайсингом называется процесс динамического изменения вот этих порогов. То есть со временем, в зависимости от флуктуации входящего потока, система тут же гибко реагирует и вот эти пороги подстраивает. То есть не получится у нас для какого-то стационарного, для стационарного-то получится настроить пороги, и она у нас будет хорошо работать. А слайсинг заключается в том, чтобы динамически менять эти пороги. Спасибо большое, да, я уже время перерасходовала. Спасибо, Сергей Николаевич.
Есть еще какие-то вопросы? Я так в заключение еще хотел сказать, что вот тут как бы, что тут еще хорошего вот в этом, подходе, то, что мы даем новую жизнь тем вот результатам, которые раньше были получены, потому что вот эти модели с резервированием, они использовались как-то раньше, но не решали эти задачи. Поэтому, так что читайте книги, много чего знаете. Хорошо, тогда я хотел бы объявить следующий доклад. Это Екатерина Маркова и еще Адоу. Я правильно говорю? Кто будет докладывать? analysis of non-preemptive scheduling for 5G network model with slicing framework. Так, Екатерина.
Я буду докладывать.
А вы будете докладывать, да, извините, я просто... Ну хорошо, тогда вы знаете, как, так сказать, активировать свою презентацию?
Да.
Да, ну хорошо. Значит, мы вас слушаем.
Good afternoon, everyone. My name is Eve, and I'd like to bring to your attention the paper on the following topic: analysis of non-preemptive scheduling for 5G network model within a slicing framework. We begin with the introduction. As you already know, recent years have seen an exponential growth of traffic in modern wireless networks. And due to that, the fourth generation wireless networks were very soon about not to be able to withstand that. In addition to that, new industries and businesses have been facing problems to be supplied with highly flexible and very controlled critical network connectivity. So as a solution, leading standards organizations in the domain of modern wireless telecommunication networks developed the brand new 5G wireless networks with the main feature slicing technology. In practice, mainly, slicing allows mobile operators to provide users with customized networks called slices with different quality of service capabilities. Thing to mention is that compared to traditional networks, this technology has a lot of advantages, but aside the use of flexible logical networks, which are, by the way, offering better performance than the so-called one-size-fits-all, there is another interesting feature in slicing. It's the isolation of network resources between all the services. And that optimizes de facto the allocation and use of the physical resources. Here we have some data from GSM Alliance to give a general view of 5G networks implementation around the globe. So you can see that, for instance, we are looking at a penetration rate up to 70% of the population by 2025 for mobile subscriber, thanks to 5G implementation, of course. Also, you can see that 5G is expected to represent like 21% of total connection by 2025 also. And so, and now some math. Okay, we considered the following queuing system model with buffer and ritual queue. And since we have two request types, we applied a non-preemptive scheduling mechanism. So here you have the scheme model and the main notation just below. The system state, the system behavior is described using a three-dimensional vector n1 n index 1 and index 2 s over the following state space x here, where n index 1 represents the current quantity of first type request in buffer, and 2 is the current quantity of second type request in virtual queue. S represents the state of the server. The corresponding state transition diagram is given here. Next, the corresponding random state transition for a random state is given. The corresponding Markov process is described by the following equilibrium equation system, where P represents the stationary probability distribution. Yeah, as you already know, the stationary probability distribution of the MM1 infinity virtual queuing system can be computed through generating function-based approach. As for our model, we tried that approach, more precisely the one used in Professor Bocharov, Apis, and Pechinkin books. And we got to a system of partial differential equations that we were not able to solve. Then we investigated the, let's say, the asymptotic analysis approach of Professor Nazarov-Tepugov from Tom State University. And for now, we were only able to conclude the first stage. If I recall, there are 3 stages, but generating function-based approach is not the only way to find the stationary probability distribution. It is also possible to use the numerical solution of the equilibrium equation system by, concerning our model, of course, by just fixing or setting all storage capacities to maximum possible. So I'd like to mention here that we showed in previous work that by significantly increasing the maximum storage capacities or sizes, we are able to find solution extremely close to a genetic function solution. So we set our buffer maximum storage capacity to n index 1 and our virtual queue maximum storage capacity to n2. Okay, so we compute the system stationary probability distribution using numerical solution with R, the infinitesimal generator of Markov process, the element of which I described using that equation. Yeah. And then we are all set. We can just compute the system main performance measures. We have the main number of first type requests in buffer, the main number of second type requests in our virtual queue, the immediate service probability of any new incoming type request, the immediate service probability of a virtual second type request, the emptiness probability of buffer, the emptiness probability of virtual queue, and lastly, the business probability of the server by first type request and by second type request. So now the numerical example. Here are the input data for our numerical example. So we illustrated the behavior of system main performance measure depending on average load pair. So we can see that the mean number of first type requests in buffer increases as the average overload increases and is not influenced influenced by the value of the second type request average overload. In contrary, the mean number of second type requests in the retrieval queue here increases as the average overload increases and is greatly influenced by the average overload of the second type request here, as you can see. So we explain this by the fact that the non-preemptive priority scheduling we use since the beginning of first type request over the second type request was the cause to that. So next we have the immediate service probability of any new incoming type request. We can see that it decreases as the average overload of first type of first or second type request increases. And here we explain this by the fact that the augmentation of the first type, the first and second type request, the quantity in system with the increase of the average overload values. So next we have the immediate service probability of retrieval second type request. Here you can see something very interesting. Let's say the peak. You can see that it increases up to a certain maximum value and suddenly decrease. So we explain this by the fact that at some point it's obvious that most of the retrieval second type requests in the retrieval queue will have more chance to quit the system after several retries. So we think that as at the peak is like the maximum of let's say the peak is the maximum level, let's say level we can reach for the immediate service probability. Here we have the buffer emptiness probability and the retrieval queue emptiness probability too. Can pretty the same. Okay, here I presented also the results for the server business probability by first and by second type request. Okay, conclusion. Okay, here we draw our I presented our results. We implemented non-preemptive scheduling in queuing system with buffer and retrieval queue, and we obtain the numerical solution of the equilibrium equation system for computing stationary probability distribution. Next, we obtain the formula for calculating system main performance measure, and we give an analysis of them. Here we draw our future investigations concerning this research topic. The bibliography is given here. Thank you very much. If you have any questions or comments, please.
Thank you very much. Any questions to speaker?
I have a question. If you said about that the network slicing allows to isolate different slices, then did you somehow define what are the metrics of isolation?
The matrix, I don't understand the matrix.
Oh, I mean, one of the key features of the slicing is that you may isolate some resource, some part of resources, some slices, so that other different type of services cannot disturb other type of services. So
I'm not sure if I get you well. You mean if we, for instance, obtain some performance measures that are related to isolation?
Yes.
Oh, no, we did not. We did not. We tried at the beginning to use, specifically intra-slice isolation, but we did not get along, so we just left it. But maybe in our next investigation we implement it. But for this one, we did not apply it.
Okay, thank you.
Thank you.
Any other questions? Maybe I ask one. Say a little more detail about the retrial, the model of retrial you are using. You have retrial queue, and what is the probability of retrial and the time between successive repeated attempt?
The average time between the retrials?
Yes, if you have retrial queue, so subscriber or request make repeated attempt with some probability.
Yes.
And how did you find the value of this probability?
No, we gave it.
Give it, and what numerically? It's
alpha in our case.
Alpha?
Yes.
Okay, and the time interval between successive retrials is exponentially distributed? Because with some probability, the request will be repeated, and the time that is needed to make a repeated attempt.
Okay, we set only alpha years as the average time interval between retrials, and
alpha. This is a probability of repetition, or
no, the time interval.
This is a parameter of time interval. Okay.
It's not the probability.
Okay. Another question is related to N1 and N2. Slide number 12. Here, maximum storage capacity is set to N1, and you are saying later that N1 tends to infinity. How did you find the correct value for N1 and N2? Because if you choose N1 not so big, it is necessary to find the accuracy of truncation. Accuracy that is related to the truncation of state space. I mean N1 and N2.
N1 and N2, we just estimated them as they approach infinity.
Approach infinity, but when you calculate the results, infinity means that you get an infinite number of equations in your system of state equation. When you solve the system by Gauss-Z alliterative algorithm, the number of equations is dependent strongly from N1 and N2.
Yes.
So if you get extremely large values, it is not possible to solve the system of state equation.
If I may ask, please, extremely large, like how much? Because okay, for what we got from the asymptotic analysis from Professor Nazarov, the solution was very close to what we obtained because we used a function called sparse in MATLAB that allow us to use very big values.
I only want to say that it is possible in some cases to find the accuracy caused by truncation.
Okay.
If we truncate the state space, it is possible to find the accuracy of truncation. The error caused by truncation by using the probability of truncated of random process that is defined on truncated state space. So if you're interested in such cases, I can send you the paper.
Yes, we are definitely interested, Professor.
Okay. So thank you very much.
Thank you very much, Professor.
If we don't have other questions, we are going to next presentation. Фаина Москалева, Екатерина Лисовская, Любовь Лапшенкова, Сергей Шаргин, Юлия Гайдамак, who will be presented the paper. Москалева, Фалина Александровна. Okay.
Do you see my presentation?
Yes.
Okay. So, dear colleagues, my name is Faina Moskалева. I'm a PhD student in Rodan University, and I want to present the paper that was prepared with junior researcher Ekaterina Lisovskaya and Professor Yulia Gaidamaka. The following slide shows the main sources that we use. The problem statement is taken from the standards, and the asymptotic analysis method is described in source 6. Network slicing allows operators to provide physical infrastructure to support various services with different requirements, and to create many service-oriented logical networks belonging to different tenants who manage slices and configure them. One of the key features of network slicing is slice isolation. The definition of degradation that we define in our work is directly related to the violation of isolation. We model the operation of the slicing manager, which distributes the total bandwidth C of the base station between the tenants of K slices. We assume that each slice is for one type of service. Let the given system receive K arrival flows corresponding to request for data transmission from users K of slices. The flows are poison with arrival rates lambda K. The system has C resource units. If there is enough free resources in the system, the customer gets up for service, the duration of which is exponentially distributed with the parameter μk, while occupying one server and bk resource unit. If there is no free resources for servicing, the customer goes to the orbit, where it carries out exponentially distributed random delay with the parameter sigma, after which it makes the next attempt to get up for service. The orbit for each arrival flow has unlimited capacity. The functioning of the system is described by a stochastic process x of t over the state space X. The state transition diagram is shown in this slide, and to find the stationary probability distribution, we derive the system of equilibrium equation in the form 1. It isn't possible to find an exact solution for this system, so we seek an approximation of the stationary probability distribution of the values of four-dimensional stochastic process. as a result of applying the asymptotic analysis method, this assumption was obtained. Approximation of the stationary probability distribution of four-dimensional stochastic process under the condition of proportionally growing delay in orbits is the product of stationary joint probability distribution and two-dimensional Gaussian probability distribution with vector of means 2 and covariance matrix 3. For the following initial system parameters, graphs show the change in the relative error between the means and variances of orbit delay parameter sigma obtained using the approximation and the simulation modeling. Thus, for example, if the infrastructure provider considers the relative error delta less or equal to 0.1 acceptable for its calculations, we see that with sigma less than 0.06, the approximation can be used to calculate the probabilistic and numerical characteristics. In the proposed mathematical model, by the degradation states of the arrival flow K, we mean the states of the queuing system, then the total amount of the occupied resources by the by the customers of flow K is less than the threshold value Ck, and the customer's number in the corresponding orbit is greater than 0. An illustration of the options for sharing the total bandwidth between the slices and degradation is shown in this slide. We defined the space of degradation states as formula 4. In order to show degradation states, a numerical example was considered. Figures show the case when sum of threshold values for each slice is less or equal to the total bandwidth. And here we show the case when sum of threshold values for each slice is more than total bandwidth. In this work, we tried to give the definitions of degradation and degradation probability from the system build. The time intervals delta correspond to the whole of the current volume of occupied resources Ck below threshold values Ck. Provided that the number of customers in the orbit is greater than 0. In total, during the observation time t, there will be nk of t such intervals, and the total time during which the slice k was not provided with ck resource units is calculated by formula 5, and we denote the degradation probability as 6. The degradation probability corresponds to the probability of the staying time for a stochastic process x of t in the degradation space, which depends on the threshold value and coincides with beta k. The degradation probability can also be calculated as 7. For a given vector of threshold values of of the degradation probability, it is necessary to find the throughput vector. We solve the optimization problem 8 by the uniform search method. Let us calculate the values of the degradation probability for all possible pairs of values C1, C2 with following parameters of the system. Then we choose such a pair C1, C2 so that the sum 11 is maximal. So the left figure is for the degradation probability of the first slide, and the right figure is for second slide. The values that satisfies condition 12 are shown in green, of which we choose a solution to the problem 11, and it corresponds to the throughput values 2 for the first slice and 4 for the second slice. On this slide, you can see the main results and tasks for further research. Thank you for your attention. I'm ready to answer your questions.
Okay, thank you very much. Any questions to the speaker?
Yes, I have a question. Good day, my name is Kirill Ageev. I have a question. Can you say what kind of services can be provided by tenants in your work?
It can be various services, for example, video conferencing, video streaming, gaming, or data transferring.
Different services, yes?
Yes, but in our model, one slice only for one service.
Okay, thank you.
Any other questions? Maybe I also ask one. Would you like to show the slide number 4? This is a mathematical model with retrials, as I see. And if you don't have retrials, this will be the multi-service Erlang model. Yes.
Yes.
It is possible to calculate the characteristic with retrials by using the model without retrials by constructing some number of approximation. Do you are using asymptotic analysis? Yes, yes, understand. Yes. And this is a explicit formulas or some numerical algorithm? You are using for calculation of characteristic. It will be algorithm or explicit formula somewhere.
Yeah, formula.
Formula?
Yes.
Explicit result.
Explicit result. Yes.
And these results presented on this slide, yes?
Yes, on this and the next slide. And it's
How
more than
A, B1, B2. This is a matrix. Two-dimensional. My question is about this. This approach is for two-dimensional model or for n-dimensional.
We use it for by using this method.
For two flows, yes.
Yes, yes.
Only two flows, yes. Okay, so I can say that exist other approximation for such model in general case when we have n input flows and it based on the multi-series Erlang formula. If you're interested in such results, I can send you the paper also.
Yes, of course. Thank you very much. I will wait for.
Okay.
For...
And these results are based on the recursive Kaufman-Roberts algorithm.
Okay.
Very quickly. And my last question is about the probability of degradation. What is it physically, technically means degradation?
Okay. I tried to say you. So by the degradation probability, we mean that we mean such states of our system then throughput value is less than some threshold value that we denote.
Okay, but this is time dependent characteristics or stationary characteristics. Okay. So you can answer later a little bit. Okay, thank you very much.
Thanks for your question.
Any other questions? No questions. Okay, thank you very much once again. So next speaker, Kirill Ageev, Eduard Sopin.
Kirill Ageev is supposed to present. Now I think he will join. He's in here.
Here, I see.
Yes. I'll try to share my desktop. Can you see the presentation?
Yes.
Yes, we see.
That's nice. Good day, everybody. My name is Kirill Ageev. I'm a PhD. What?
It's on slide 5. Could you please take it to the first slide?
Wait a minute.
It's okay now.
Okay. I present to your attention a report on the topic on the convergence of an iterative method for approximate analysis of a resource queuing system with signals. This work was prepared with Eduard Sopin. This slide lists the sources that were used in the during the preparation of the work. Let's start. At the beginning, I'll tell about the model with signals, then about our assumption with the proof of the convergence of an iterative method for approximate analysis. Then I'll describe the performance metrics. After it, I'll speak about case study and finally conclusion. We considered a multi-server queuing system with n servers, in which arriving customer occupies not only a server but also a volume of limited resources. the total volume of resources in the system is R, and volumes of customers' resources requirements are independent, identically distributed random variables with cumulative distribution function fx. Customers arrive according to the Poisson process with intensity lambda, and the service times have exponential distribution with the rate mu. Each customer in the system produces a flow of signals. Signals arrive according to the Poisson distribution too with intensity gamma. When a signal arrives, the customer releases the server and occupied resources and goes to the system again with new resource requirements. It follows that customers leave the system with intensity mu plus gamma and returns back with probability gamma divided mu plus gamma. And we make an assumption one, that to simplify our model, we make an assumption. Customers which arrive with signal contain a new type of customers with intensity tilde n gamma, where tilde n is an average number of customers in the system. Denote customers types as L. Type 1 and type 2. And in early works, we developed approximation algorithm for calculating performance metrics. This algorithm based on recurrent computing of tilde n until the difference between meanings of it become enough small. To make a mathematical substitution for this method, introduce function 9, where blocking probability PB is in formula 10. Then we have a lemma that equation x equal that x has a single solution and can be found this solution by fixed point iteration. And next slides will be about proof of the lemma. Consider the case in which the resource requirements of the redirected customer due to the arrival of the signal have the same distribution as the primary customer. Then in approximate model, we see formula 11, where offered load rho looks like on the slide. From here follows the average number in the system as formula 12. Thus, the average number of customers in the system is subject to the expression 13. Then we must calculate the derivative of function zx. Then we must take into account that offered load will look like on this slide. Then we see the derivative of function zx like formula 15. Let us now estimate the derivative of PB. From physical consideration, we can conclude that blocking probability is above 0, equal or above 0, because with increasing offered load, blocking probability couldn't decrease. We introduced an additional notation formula 16, where G rho makes sense of normalization constant. It's easy to see that the expression for the probability of blocking probability looks like formula 17 and its derivative formula 18. Then we estimate each of each of sides blocking probability. Formula 19, and it's easy to see that the expression on the right represents the mathematical expectation of the number of applications in the resource queuing system. Then turn to the second term of the expression for PB, for blocking probability. And then taking into account the obtained relations, the expression for blocking probability looks like formula 22. The expression in parent represents the positive variance of the number of customers in the system, which means formula 23. Substituting the resulting estimate in the expression for derivative zx, we get 24, and this is a sufficient condition for contraction which was required to be proved. Then I'll speak about performance metrics. On this slide we represent stationary probability by formula 25 and 26. Formula 27 defines a normalization constant with initial values 28. And here you can see the formulas for performance metrics. It is the blocking probability of customers with type 1 and 2. Formula 29, average number of occupied resources, it's formula 13. And average number of customers in the system, formula 31. Figure 3 shows the approximation algorithm for calculating performance metrics. Before start, we must define mean diff as the accuracy threshold for average number of customers. At the beginning of approximation, we have only first type of customers, and we calculate average customers number in the system with first type of customer, and denote it as previous tilde n. Having tilde n, having the second floor, we can of customers, we can calculate input parameters for second type of customers and calculate it for two flows of customers with intensity intensity lambda and previous tilde n gamma. On the next step, we compare the difference between tilde n and previous tilde n according to the accuracy threshold mean diff. If the difference less than mean diff, we calculate blocking probability of newly arriving customers, blocking probability for second type of customers, and average amount of occupied resources. Else return to denoting tilde n and calculate it with new intensity of the second floor. And now about the case study. For case study, we took 200 resources, 100 servers. Intensity of customers arriving is variety from 20 to 60. Serving intensity 1 and intensity of signals incoming is 5. We use the geometric distribution for resource requirements. And we studied two cases, equal parameters for arriving and accepted customers and different parameters for them. You can see it on this slide. P1, P2. And here you can see the result. We can say that the error between our assumption, a simplified model, and simulation model is small, and we can try to get result with this simplified method. And in conclusion, I want to say that in this paper, the mathematical justification of the application of the approximate model is given based on the numerical experiment in comparison with the result of simulation modeling. It's concluded that algorithm can be used to calculate the probability of blocking on blocking on arrival customers and average number of customers in the system and the average amount of occupied resources, since the calculation error is from 5 to 10%. In our further work, we plan to implement a more accurate analysis of the analytical model with signals. Thank you for your attention and your questions.
Okay, thank you very much. Any questions to the speaker?
Can I ask, please? Kirill, you use simplified model. So the question is, what is the reason for using simplified model? What is the need for it?
We have problems with calculating performance measures for our base model because to calculate it we must use convolutions, and it takes a lot of computing resources for it, and we tried to solve this problem.
Okay, thanks. It's clear.
Any other question? Maybe I was asked one. Here I see calculation error is from 5 to 10%. It's a relative or absolutely?
Relative error.
And you obtain these results only for what are assumptions concerning the getting of this result? What can you say about the generality of this result? This is, of course, this is not total recommendation. This recommendation is restricted by your assumption concerning the simulation. Yes.
Sorry, maybe I'm not understand your question, but can you repeat, please?
You obtain quite good results, 5%, 10%, and these numbers are you obtained only for restricted assumptions. What kind of assumption was made concerning the simulation? You are using. I see geometric distribution. If
yes.
The distribution will be another, what can you say about the result?
We tried to use another distribution, but I'm not sure that the relative error was higher. But if it's necessary, we can use another distribution and calculate our and apply our method for it in future. Okay.
It will be necessary if you are going to defend your theses, because the generality of results should be proved in numerically, of course. Okay, thank you very much. Следующий доклад Степан Рогозин. Generalized loss priority system with application to bandwidth sharing.
Видно презентацию, да?
Видно, да.
Так, ну, я на русском языке буду докладывать, но слайды у меня на английском будут. Значит, тема моего доклада, значит, обобщенная система потерь с приложением к системам разделения полосы. сначала рассмотрим систему, предложенную Вардом Виттом. В данной системе есть n станций, и каждая станция имеет S и T серверов, то есть число серверов в станциях может быть разным. Также существует C классов заявок, и заявка класса G требует только один сервер на каждой станции из подмножества серверов A и J. Заявка класса J следует по соновскому потоку, он прибывает с поссоновским потоком с интенсивностью лямбда J, и времена обслуживания имеют общее распределение с конечным средним. Данная система описана в книге Варда Витта 1985 года. И вот такие результаты там представлены. Если мы обозначим за nj, это стационарное число заявок класса J в системе, и nj с бесконечностью – это стационарное число заявок в такой же системе при условии, что существует бесконечное число серверов, то можно получить распределение вероятностей числа заявок в системе с помощью данных формул, то есть выразить распределение вероятностей в системе, где число серверов ограничено, через вероятности, в которых число серверов бесконечно. Значит, а для этой системы уже известно данное распределение. Вот оно представлено ниже, здесь. Значит, теперь рассмотрим еще одну систему. Но эта система должна быть всем известна, то есть это обычная система разделения полосы. То есть заявка класса K требует kt единиц базовых цифровых каналов, где K может быть от единицы до K большого. И значит, заявки приходят с интенсивностями лямбда K и с экспоненциально распределенными временами обслуживания. Ну, данные системы вот у Башарина Гелия Павловича представлены, и также у него есть ссылка на книгу Росса, где также данная система есть. И для удобства, чтобы говорить о данной системе, я впоследствии буду называть системой Башарина. Значит, здесь известные формулы из данной книги. Так, и, значит, мы рассматриваем, значит, следующую систему. Система Виттов, которую я упомянул в начале, может быть представлена как мажорирующая система к системе Башарина. Данным способом мы разбиваем на подклассы число этих подклассов, это число сочетаний из n по bk, то есть таким образом, чтобы то есть мы разбиваем входной поток заявок на подзаявки таким образом, чтобы мы могли воспользоваться формулами Витта. То есть мы фиксированно знаем, какие заявки идут на какие сервера. И можем ввести вот для каждого подкласса обозначить AJ, то есть множество станций, на которые подкласс J может прийти. Значит, ну, в данном случае у нас в каждой станции будет по одному серверу. Значит, когда мы провели моделирование данной системы, оказалось, что вероятности потери слишком сильно превышают вероятности потери в исходной системе. И мы ввели некоторую модификацию, то есть топологически расположили сервера таким образом, что у нас на каждой станции примерно одинаковое число серверов, а число станций определяется максимальным значением заявки. То есть это будет работать для тех систем, где число серверов большое, а заявки маленькие, то есть требуют малое количество серверов. То есть здесь мы просто расположили те сервера, которые у нас остаются, то есть таким образом, чтобы они были в среднем примерно одинаковые в каждой станции. Здесь у нас по оси абсцисс станции, по оси Y как бы количество серверов в станциях. Значит, результаты моделирования здесь представлены здесь сначала для 3 серверов, но они довольно близкие оказались. Значит, ну, сплошная линия — это система Вита, значит, точечная, да, это система Башарина в черточку. Для 10 серверов уже довольно существенное отклонение идет, и это для общего РО, то есть вот по такой формуле рассчитывается. Но да, стоит сказать, что здесь рассматривается пример, в котором первый класс требует 1 сервер, второй класс требует 2 сервера, а в сумме у нас всего 10 серверов. Ну, для 20 серверов и для 30 серверов, в принципе, почти то же самое, то есть не наблюдается сходимости. Далее мы рассматривали, провели моделирование для различных значений, для различных времен обслуживания в системе Башарина. Значит, для экспонента вот это обычная линия синяя, но остальные, как оказалось, они лежат ниже вероятности потери. Система Вита, однако, ну, довольно намного их превышает. Здесь это для подкласса, для класса 2. И здесь мы добавили 3-й класс заявок. Это вот, ну, фиолетовая линия. И, в общем, видно, что она стала еще выше. Ну, и далее там она увеличивается с увеличением класса заявок, но при этом стоит отметить, что мы рассматривали, делали моделирование для 20 серверов, то есть для небольшого количества. Здесь график, то есть у нас RO1 это интенсивность трафика заявок класса 1, ρ2 это интенсивность трафика заявок класса 2. Видно, что в некоторых случаях вероятности потери довольно близки между системами Витте и Башарина, но кое-где они весьма различаются. Здесь это вероятность потери для второго класса. Ну, значит, в заключении можно сказать, что значит, вероятности потери всегда превышают вероятности потери в системе Башарина. Но это аналитически пока мы не показали, но интуитивно это показывается достаточно легко. То есть там легко показать, что потерь будет больше. Вот. Но, значит, они все-таки оказались довольно неточными, да, верхней границы, но тем не менее для общих времен обслуживания можно использовать вот данную систему. Так. Да, у меня все. Спасибо за внимание.
Так, хорошо, спасибо большое. Есть ли вопросы к докладчику? Знаете, я вот спрошу вас. Вот у вас название Generalized Lost Priority System. А где у вас тут приоритет?
Ну, здесь, да, здесь нету. У меня в статье есть еще описание систем с приоритетами. Они тоже...
Понятно. Так, ясно. Хорошо, еще вопрос. Вот у вас здесь N, да? N это число...
Да, станций. Угу.
А БК это что такое?
БК это, получается, число базовых цифровых каналов, которые...
А вот у вас там, знаете, есть вот на 6-м слайде, по-моему, вы берете C из N по БК. Вот N это, то есть БК это требование к ресурсу, а N это что такое? Это ресурс или это не число потоков случайно?
Нет, это число, здесь число станций. Почему? Потому что здесь в каждой станции по одному серверу. Но вот, как я уже сказал, вот это как бы одна из систем, которую мы рассматривали, но там оказалось вероятности потери слишком...
Просто странно, вот это БК это ресурс требуемый, да?
Да.
А вверху это...
Ну, как бы число
это должно, они должны быть соразмерны, там, ну, ресурс и ресурс. N же это не ресурс.
N это число станций, но в данном случае это и число серверов. То есть общее число ресурсов.
Ну ладно, это так. Ну, еще вопрос, а в чем состоит вот ваш результат? Вы, ну, есть как бы модель Вита, есть вот эта модель, ну, это вы назвали ее Башарина, на самом деле эту модель, там, да не, так сказать, она известна давно довольно. Это вот есть такие авторы, Кауфман и Робертс, они опубликовали вот этот алгоритм рекурсивный для расчета этой модели. Вот Рост, кстати, ссылается на него. А на самом деле еще до Кауфмана и Робертса, еще лет 10 до них были результаты получены для этой модели, вот, которая здесь вот существует. Так, и здесь вот эта, кстати, модель, она справедлива. Вот вернитесь обратно немножко. Вот вы пишете, значит, время обслуживания экспоненциально распределено. Здесь время обслуживания может иметь любое распределение, не только экспоненциальное.
Вот в данной модели, да?
Да, вот эта модель, когда это мультисервисная модель Эрланга, и она, результаты, которые там получены, справедливы для любой Ну, естественно, что время распределения должно быть одинаково, но оно может быть произвольным. Но так же, как и обычная формула Эрлана.
Ага, но вот когда я проводил моделирование, то для системы Башарина как раз, то для некоторых распределений они действительно совпадали, но вот если посмотреть на Паретто, ну, здесь перепутаны эти цвета, но вот Паретто 1 и 2 вот здесь внизу идет, оно значительно отличается.
Ну, не должны. А вы имитационное моделирование делаете?
Имитационное, да.
Ну, может быть, ошиблись. Нет, они, так сказать, распределение, от функции распределения не зависит. И у меня вопрос такой, а в чем результат стоит? Вот вид, модель Витта, там можно посчитать характеристики. И вот то, что вы называете модель Башарина, тоже можно. Вы что, просто хотели сравнить? Или там просто считается сложно, Башарин проще?
Там получается, что да, мы хотели сравнить, и там вот я не знаю, еще раз посмотрю, но у Башарина там не было написано про общие времена обслуживания. То есть мы думали, что с помощью ВИТа можно будет получить оценки для общих времен обслуживания.
Нет, ну это общее. Если хотите, я пришлю ссылку.
Хорошо, спасибо. Да.
Хорошо. Спасибо большое, докладчик. Если нет других вопросов, тогда мы... Да, кстати, я еще продолжу. Вот это как бы результат можно рассматривать не только... Здесь вот вы рассматриваете просто мультисервисный узел, а можно рассматривать и сеть, там произвольное число слов, и там есть алгоритмы, примерные алгоритмы и так далее. Ну ладно, я еще раз благодарю всех докладчиков, гостей. Думаю, что сессия прошла плодотворно, было много вопросов, люди познакомились друг с другом, ну и теперь будут представлять работы не только по письменным свидетельствам, но и так и визуально. Ну хорошо, тогда всем еще раз до свидания. Закрываем, да, Эдуард Сергеевич?
Да, хорошо. Присоединяюсь к Сергею Николаевичу. Спасибо всем.